Hello there, and welcome to Physics with William, where curiosity settles in gently and science takes its time. Tonight we're turning our attention to something so ordinary that it rarely gets a proper introduction, and yet it is one of the strangest events in your entire day. You open your eyes, glance around the room, and the world appears. A wall, a lamp, a cup on the table, the outline of a window, perhaps a book left slightly open as if it had been interrupted mid-thought. All of it arrives with such ease that it feels almost natural to assume that seeing is simple. Of course you see. You have eyes. The room is there. Problem solved. And yet the closer you look at that everyday miracle, the more peculiar it becomes. Because what does it actually mean to see something? Not in the loose, casual sense. Not just to notice it, recognize it, or remember where you left it. I mean in the physical sense. What exactly happens between the thing out there and the experience in here? How does a quiet object sitting across the room become a vivid image in your awareness? What is actually travelling? What is being measured? What is being transformed? And how does the universe manage to turn light into a world that feels immediate, stable, and almost absurdly effortless? Before we go much further, I would love to know where you're listening from tonight, and what is in front of you right now. Not what should be there, but what is there. A ceiling, a screen, shadows in the corner, a sleeping pet who has somehow claimed more than their fair share of the bed. It seems like a simple question, but it is a fitting one for a night like this, because whatever you're looking at has already begun a remarkable little journey. And if this slow wander through the physics of sight brings you some calm, or keeps you company while the day winds down, do consider liking the video and subscribing. It helps this quiet corner of science reach other people who might appreciate a softer landing at the end of the day. Now then, let us settle in and take this apart carefully, because the moment you see anything at all, far more is happening than the eye alone would have you believe. The first thing to notice is that seeing does not begin with your eye in the way people often imagine. The eye matters enormously, of course. We will give it its due. But long before the eye enters the picture, physics is already busy setting the stage. Light must exist. It must travel. It must encounter matter. It must leave behind traces of what it met, and only then can your body begin to do its part. In that sense, seeing is not a private act sealed inside your head. It is an interaction between you and the outside world, conducted by light, shaped by matter, and refined by biology into something we casually call vision, as if that explains anything at all. Take the simplest case you can imagine. There is a mug on a table. You look at it and say that you see the mug. It feels as though your gaze goes out and finds the object, rather like a polite little search party. But that is not what is happening. Your eyes are not sending anything outward to touch the mug. They are receiving. The information comes in. Something from that mug, or more precisely, something about the way light has interacted with that mug, is arriving at you. Without that arriving light, the mug may still be there, solid and patient and completely unbothered by your confusion, but you will not see it. The room could be full of objects and your eyes could be open, yet in total darkness there is no vision to speak of. That alone tells us something important. Seeing is not just about having eyes. It is about receiving light that has been altered by the world. This is where the story begins to get a bit sly. We often talk about objects as though they possess their visible qualities in a direct and permanent way. The apple is red, the leaf is green, the book is blue, the wooden table is brown, and for daily life that is perfectly useful. No one wants to be the person at dinner who asks to pass the object currently favouring the longer wavelengths of reflected light. That is how one ends up eating alone. But from a physics point of view, colour is not sitting inside the object like a hidden filling in a pastry. What the object really does is interact with incoming light in selective ways. It absorbs some parts, it reflects others, it scatters others still. The light that finally reaches your eye carries the outcome of that interaction. In other words, The visible world is not made of objects handing over neat little labels. It is made of matter continuously modifying light. That is already a strange way to think about the room around you. The lamp beside the bed is not simply lamp-shaped and lamp-coloured in the way your experience suggests. It is a surface with a particular structure, made of particular materials, arranged in such a way that incoming light is redirected into space according to the rules of electromagnetism. Some of that redirected light happens to enter your eye. From that, your visual system will eventually produce the impression of shape, colour, texture, location, and perhaps even mood. Soft lamplight, hard edge, glossy ceramic, faded cloth. Yet none of those impressions are floating freely out there in complete form. The physics begins with light and matter. The richness comes later. Now, when we say light, it is worth slowing down just a little, because the word is so familiar that it can become almost empty. Light is not merely brightness in the vague sense. It is a physical thing in motion, a form of electromagnetic radiation. That sounds grand and slightly overdressed, but it simply means that light is made of oscillating electric and magnetic fields that move through space. Sometimes it helps to think of it as a travelling disturbance, a carrying of energy from one place to another. Sometimes it helps to think of it in terms of particles called photons. Both descriptions are useful, and physics rather inconveniently insists on keeping both around, because light behaves in ways that require each of them. It is one of the earliest signs that the universe does not always care whether our preferred metaphors are tidy. For the purposes of seeing, though, we can start with something modest. Light comes from somewhere. Perhaps the sun, perhaps a bulb, perhaps a screen glowing in the dark while everyone promises themselves just one more video before sleep. That source sends light outward in many directions. The light spreads, moves across the room, and meets surfaces. When it strikes the mug, the table, the curtain, the wall, it does not merely bounce like a rubber ball with perfect obedience. It interacts with the atoms and electrons in those materials. Some frequencies are absorbed more readily. Some are re-emitted or scattered. Surface roughness changes the direction of travel. Transparent materials bend the path. Shiny materials preserve more orderly reflections. Matte materials scatter light more diffusely. Every visible object in the room is continuously participating in this traffic of light, taking in some and sending out some, each according to its structure. That phrase structure matters more than it first appears. Matter is not passive here. The reason glass behaves differently from wood and water differently from paper is not because the universe enjoys variety for its own sake, though it does seem to have a flair for it. It is because the internal arrangement of charged particles in a material determines how that material responds when electromagnetic fields pass through or strike it. Light encounters electrons bound within atoms and molecules. Those charges respond. They shift, vibrate, re-radiate, or resist. From those microscopic responses emerge the visible behaviours we know so well. Reflection, refraction, absorption, transparency, opacity, colour, gloss, haze, the look of a polished spoon versus a knitted blanket, the deep still darkness of velvet versus the bright insistence of white paper. Physics is already at work before the eye ever takes its first sip of the scene. And then there is the astonishing fact that only a tiny slice of all possible electromagnetic radiation is visible to us at all. The universe is full of radiation beyond human sight. Longer wavelengths, shorter wavelengths, entire regions of activity moving silently through the world with no direct announcement to our senses. Radio waves pass through walls, infrared carries heat, ultraviolet can alter skin and molecules, X-rays pass through tissue in ways that still sound like a magic trick until one remembers the hospital bill. Yet your eyes respond to just a narrow band, a little sliver of the electromagnetic spectrum. That is what we call visible light. From a cosmic point of view, it is a rather specific arrangement of sensitivity. We do not see all that exists. We see what our biology evolved to catch, and what it evolved to catch happens to align with the light that reaches the surface of our planet in particularly useful ways. That should make the act of seeing feel a touch less obvious, and a great deal more contingent. The world you see is not the universe in full. It is the portion of reality filtered through the physical limits and biological design of your visual system. Even before the brain interprets anything, selection is taking place. Certain wavelengths are admitted into your experience. Others are left outside the gate entirely. Your eyes are not open windows in the absolute sense. They are tuned instruments, and like all instruments, they leave plenty out. Still, what they do include is enough to build a world of extraordinary richness. Think for a moment about how much information arrives when you simply glance around a room. Edges are separated from backgrounds, distances are suggested, surfaces differ in brightness. Motion, if there is any, announces itself quickly. A face can be recognized in an instant. A book can be located on a shelf. A cup can be judged empty or full, or worse, discovered to contain tea gone cold long before anyone had the decency to warn you. Sight gives the impression of immediacy, and that impression is so persuasive that it can hide the underlying complexity. Yet everything begins with raw physical events, light sources emitting radiation, matter reshaping that radiation, photons arriving, optical structures guiding them, receptors responding, signals changing form. What is remarkable is not merely that this chain exists, but that it happens continuously and at scale. At every waking moment, unless you are in darkness or your eyes are closed, an immense number of photons are entering your eyes. Not one at a time in some neat little queue, but in torrents. They come from every visible surface around you. From the ceiling, the floor, fabric, skin, dust, glass, paper, metal. Some have travelled from nearby lamps. Some began their journey at the sun and scattered through the atmosphere before ever reaching the object you're now looking at. Others have reflected several times before arriving. Light does not politely introduce itself with a name tag and origin story. It arrives as a flood of physical possibility, and your visual system has the demanding task of turning that flood into an orderly experience. When people first learn a little about vision, they sometimes imagine that the eye takes a sort of miniature picture of the world and sends that completed image inward, rather like posting a postcard to the brain. It is a tempting picture because it feels simple. The eye is the camera, the brain is the viewer. Job done. But the truth is more layered. The eye does form an image through optics, yes. Light is gathered and focused. The scene is projected onto the retina at the back of the eye. But that is not the end of the work. It is barely the beginning. The image on the retina is not yet what you consciously experience as the visible world. It is only a physical arrangement of incoming light across a living surface, already filtered, already limited, already upside down in optical terms, and already awaiting further transformation. The world you feel yourself to be looking at is the result of processing, comparison, compression, enhancement, correction, and interpretation. Physics hands biology a stream of structured light. Biology then makes vision out of it. There is also something almost comical in how indirect the whole process really is. You never touch the object with your sight. You never pull its redness, its brightness, its texture straight into your mind. You receive light that has interacted with it, and from that you infer. Your visual system infers astonishingly well, so well that the result feels direct. But it is still inference. The world sends clues. Your body builds a case. Under normal conditions, the case is strong enough that you go about your day with confidence, stepping around furniture, reading signs, identifying faces, and locating biscuits with admirable reliability. Yet the reliability can fool us into forgetting that sight is an achievement, not a given. Consider what has to be true for the sentence, "I see the room," to make physical sense. There must be some source of illumination, unless the objects themselves emit visible light. There must be a path through space from source to object and from object to eye. The medium between them must allow the relevant light through. The light must survive travel without being completely absorbed or blocked. The surfaces must reflect or emit in the appropriate ways. The structures of the eye must be transparent enough to admit and focus light. The retina must respond. The signals must be transmitted onward. All of that must happen for something as casual as noticing the edge of a chair in dim evening light. The ordinary world is full of events so reliable that they become invisible as events. Vision is one of the clearest examples, and yet the reliability is only partial. There are shadows, glare, poor lighting, fog, after-images, blind spots, optical illusions, and all manner of ways in which seeing reveals its constructed nature. Even in the most routine glance, the world does not arrive in perfect completeness. Your eyes move constantly. Details sharpen in some places and blur in others. Brightness depends on contrast. Colour depends on context. What seems obvious can change if the light changes. A white shirt at noon and the same shirt in warm evening light do not send identical light into your eyes, but you often experience them as the same shirt anyway. That means vision is not a straightforward reading of physical data. It is a negotiation between the incoming light and the systems built to make sense of it. For tonight, though, we do not need to leap too far ahead. It is enough to stand at the threshold and notice the first principle clearly. Seeing begins when light, shaped by the world, enters the body. Not before, not by magic, not because objects simply push their appearance outward into your awareness, and not because your mind reaches out and grabs them. The process starts with light in motion, and with matter that alters its path. That is the physics of the first step. So the next time you glance at something familiar, perhaps the corner of your room, the outline of your hand, or the quiet glow of the screen in front of you, it may help to remember that nothing visible arrives all at once as a finished fact. A source emits, a surface responds, light travels, your eye receives. That ordinary instant is built from interactions smaller and stranger than your experience lets on. The room is not merely there in a visual sense. It is continuously sending evidence of itself through light, and you are continuously gathering that evidence. From here, the question becomes even more interesting, because once that light has left a surface and started toward you, what exactly is it doing on the way? What sort of thing is a photon really in this story? And how does the outside world manage to hand over just enough physical information for an eye to begin building sight at all? If seeing begins with light arriving, then it is worth asking a very simple question that quickly becomes much less simple. What exactly is making that journey? What is moving from the lamp to the table, from the table to your eye, and from the stars to the small observatories in our heads that call it sight? We use the word light so casually that it often sounds like an atmosphere rather than a physical event. A room is full of light. The morning light is soft. The kitchen light is too harsh. The screen light is keeping me awake again. All of that is perfectly sensible in daily life, but beneath those ordinary phrases sits something far stranger. Light is not merely brightness filling space. It is energy moving through the world in a very particular way, and when we follow that movement closely, the whole business of seeing starts to look less like passive observation and more like a relay of remarkable precision. Let us begin with the idea of a photon, because that is the name most people meet first when they ask what light is made of. A photon is the particle description of light, though even saying that requires a small warning label. If you imagine a photon as a tiny glowing bead flying through space like a very determined grain of dust, you will understand a little and misunderstand quite a lot. Physics, with its usual talent for being both illuminating and mildly inconvenient, tells us that light does not behave only like a neat little particle. It also behaves like a wave. At times it spreads, interferes, overlaps, and diffracts in ways that no ordinary pellet or marble has any business doing. At other times it arrives in discrete packets of energy, detectable as individual events, as though the wave had gathered itself into countable units. This is not because light cannot make up its mind. It is because our familiar categories are not quite built for the task. The photon is real and useful, but it is not a tiny bullet in the everyday sense. Still, for the purpose of following the journey from object to eye, the photon is a very helpful travelling companion. It allows us to speak about light as something that can be emitted, absorbed, scattered, redirected, and eventually caught. A source of light emits photons. A surface reflects some photons and absorbs others. Your retina catches incoming photons, and that catching begins the chain of events that will later become vision. In that broad sense, the story is simple enough to tell while you're half asleep, which is fortunate because that is often when the best physics settles in. Now, where does a photon come from? Not out of nowhere, although the universe is fond of looking like it has produced things from nowhere when viewed from a great enough distance and a poor enough angle. A photon is emitted when energy changes form in a way that allows electromagnetic radiation to be released. In an ordinary light bulb, electrical energy is used to heat a filament until it glows, sending out a broad range of radiation that includes visible light. In a light-emitting diode, electrons move in a material and drop between energy states in a way that produces photons more directly and efficiently. In the sun, the story is grander and far less local. Deep within its interior, nuclear processes release enormous amounts of energy, and after a complicated and staggeringly long internal journey, some of that energy eventually emerges from the surface as sunlight, spilling outward across space in every direction. A little of it reaches Earth, where it pours over clouds, oceans, rooftops, curtains, cups, leaves, faces, and the backs of hands held near windows. Some of it will eventually enter your eyes. A photon that helps you see a spoon on your kitchen table may be part of a story that began in a star. That alone ought to make washing up feel slightly more dignified. Once emitted, the photon does not need a road, a rail, or a breeze to carry it. Light travels through empty space. That is one of its great distinctions. Sound needs a medium. It depends on matter vibrating, whether air, water, or something solid. Take the air away and sound is silenced. Light is different. As electromagnetic radiation, it can propagate through the vacuum of space. That is why sunlight can cross the emptiness between the sun and Earth. No cosmic wind is shoving it along. No invisible corridor is guiding it. The propagation is built into the nature of the electromagnetic field itself, which is a rather elegant arrangement when one thinks about it. The universe did not merely produce stars, it produced a way for their energy to travel immense distances and still arrive meaningfully somewhere else. The speed at which light travels is famous enough to have escaped physics and entered ordinary speech. We use it as shorthand for very fast indeed. But in the context of seeing, that speed matters in a more intimate way. Light travels so quickly that for everyday distances it feels instantaneous. The lamp on your bedside table sends light to your eye in a tiny fraction of a second. The moonlight reaching you has travelled a little over a second. Sunlight takes several minutes. Starlight may have been travelling for years, centuries, or far longer before it reaches a telescope or a human retina. So when you look around a room, the tiny delays are too small to notice. When you look at the sky, you are already looking into the past. Vision is always reception after travel. It is never direct contact with the present moment in the absolute sense people often imagine. That may sound dramatic, but it is really just a consequence of finite speed. If information travels, then information arrives after a delay. Usually the delay is negligible on the scale of your bedroom, kitchen, or local supermarket queue, though some queues do seem to produce distortions in time of a distinctly personal nature. Yet physically, the delay is always there. A visible object cannot be seen until light from or about that object reaches you. The journey may be very short, it may be immense. Either way, the light must travel. What happens along the way depends on what the photon encounters. If it passes through empty space, its path can remain uncomplicated. though even then gravity can bend the route on very large scales. If it moves through air, it may travel largely unhindered, but air is not truly nothing. Molecules, dust, water droplets, smoke and changing density can all alter how light behaves. That is why fog softens the world. It does not erase objects. It scatters the light coming from them, redirecting it so broadly that clear edges and distant details become harder to recover. It is why a dusty room can reveal shafts of sunlight that are ordinarily invisible. The light was always there, but the floating particles now scatter some of it toward your eyes, drawing visible lines through the air, and it is why sunsets redden. As sunlight passes through more atmosphere, shorter wavelengths are scattered away more strongly, leaving the longer ones to dominate the direct light that reaches you. The sky itself becomes a record of what the light has survived on the way. Even in a room, the photon journey is rarely as tidy as source to object to eye. A beam from a lamp may strike a wall, scatter into the room, bounce from a table, reflect off a glass, and only then head toward you. Some photons reach your eyes after several encounters. Others are absorbed and never continue. Others pass through transparent materials and emerge bent. Others are scattered so diffusely that their exact past becomes hopelessly tangled. This is worth lingering on because it means that seeing is not built solely from pristine direct rays carrying simple reports. Much of what you see depends on a complex traffic of light interacting with many surfaces before the final approach. Rooms are visible not merely because light sources shine, but because light ricochets, diffuses, fills corners, and redistributes itself across space. That redistribution is one of the reasons a room with one small lamp can still be broadly visible rather than divided into one bright patch in universal oblivion. Photons leave the lamp, strike walls and objects, then scatter onward. Each visible surface becomes, in effect, a secondary source, not because it generates light from scratch, but because it sends some onward after being illuminated. This is how the world borrows light. Most of the things you see are not luminous in themselves. They are borrowing from some source and returning altered portions of that gift. A black coat returns little. A white page returns much. A red apple returns certain wavelengths more strongly than others. A mirror returns light in a more organized way, preserving directional structure that allows images rather than mere illumination. That difference between rough scattering and orderly reflection lies behind the difference between seeing a bright wall and seeing yourself in a polished spoon, while wondering why your face looks like it has been wrapped around a turnip. At the microscopic level, this interaction is not a matter of light bouncing off surfaces like rubber balls from a pavement. The atoms and electrons in the material respond to the electromagnetic field of the incoming light. Charges move, energy may be taken up, re-emission may occur. Collective behavior across vast numbers of particles gives rise to the visible phenomena of reflection, absorption, transmission, and scattering. The surface you casually call shiny or dull is behaving according to an intricate arrangement of matter. A polished metal can preserve directional information because of how free electrons respond across a smooth surface. A matte wall scatters light broadly because of microscopic roughness and material structure. Glass allows visible light through because its electrons do not absorb those wavelengths strongly in the visible range, though the light does slow and bend as it passes. Water does something similar with its own quirks. Leaves absorb strongly in some bands because of pigments involved in photosynthesis. Skin, cloth, paper, ceramic, cloud, milk, dust and snow each handle light differently. To see is to benefit from all that selective behavior. The photon itself, however we choose to picture it, carries energy. That energy depends on the light in question. Visible light is not all identical. Different colours correspond to different energies and wavelengths. Red light differs from blue light not because one has decided on a different personality, but because the oscillations and the photon energies differ. That difference matters both for how matter interacts with light and for how your visual receptors later respond. A blue pigment may absorb longer wavelengths and reflect shorter ones. A red surface may do the opposite. The incoming mix from the light source and the selective response of the material together determine what finally continues toward your eye. So when you say that something looks red, you're usually describing the result of a filtering process, not an intrinsic glow of redness stored inside the object. There is also the matter of direction. For you to see an object, photons related to that object must arrive from the direction where the object is located. This seems obvious until one realizes how much the structure of vision depends on it. If light from every part of the room arrived at your eye in a hopelessly mixed jumble with no directional order, there would be illumination but no image. The ability to see shape and location depends on the geometry of incoming light. Different points on an object send or redirect light into different paths. The optics of the eye preserve enough of that directional structure to form an organized image on the retina. That is why the journey of photons matters not only as a transfer of energy, but as a transfer of spatial information. The light arriving from the top edge of a book must remain distinguishable, in path from light arriving from the table beside it. Without that organization, the world would wash together into a brightness without form. This is where the invisible journey becomes almost paradoxically visible in its effects. You never see the photon itself on its way through ordinary empty space. You see what happens when it's emitted, scattered, reflected, absorbed, or detected. A beam of light in clean air is mostly invisible from the side. Shine the same beam through smoke or dust, and suddenly it appears as a line because particles are now scattering some of that light toward your eyes. The path was there in both cases. Only in one case was there enough side scattering to make the route visually apparent. In a sense, photons reveal themselves most readily when their journey is interrupted. That interruption is not failure. It is the whole basis of visibility. Objects become visible because they interrupt the onward progress of light in particular ways. A perfectly transparent object with no scattering and no absorption would be very hard to see. If it altered nothing about the light passing through, it would leave no visible clue. Real transparent objects are visible because they bend light, reflect a little, absorb selectively, or possess edges and impurities that reveal them. A glass of water is seen not because glass and water loudly announce themselves, but because they modify light subtly enough for your eye to recover their presence. Seeing is never just receiving light, it is receiving altered light. We should also be careful about the idea of straight lines. In ordinary conditions, we often say that light travels in straight lines, and for many practical purposes that is true enough to build a room, design a camera, or explain why shadows fall where they do. But physics adds footnotes. Light bends when it passes between media of different optical density. That is refraction. It can spread around edges. That is diffraction. It can reflect. It can scatter. In strong gravitational fields, even empty space is not a perfectly neutral stage, and light follows curved paths through curved space-time. None of that ruins the simpler picture, but it does remind us that the invisible journey is governed by physical conditions rather than by a universal promise of straightness. Imagine, then, a single visible moment. You glance at a page, light from a lamp or the sun travels outward. Some of it reaches the page. The white regions of the paper scatter much of the visible light back out. The black ink absorbs more and returns less. That difference in returned light carries the pattern of letters. Photons travelling from the bright paper and the darker ink head in many directions, but some paths lead to your eye. The lens system of the eye will soon sort those incoming rays into an image. The retina will register contrasts. The brain will extract edges, shapes, and finally language. But before any of that, there was simply the photon journey. Emission, travel, interaction, travel again. Without it, there is no page to read, no line to follow, no quiet sentence reaching the inside of your mind. What makes the story more astonishing is that none of this requires intention from the light. A photon does not know it is on its way to help you see a page, a face, a tree branch, or the faint crack in the ceiling you have been meaning to ignore more decisively. Physics does not proceed by meaning. It proceeds by lawful behavior, and yet lawful behavior, repeated across unthinkable numbers of photons and shaped by the structures of eye and brain, gives rise to a world that feels rich with meaning. Sight begins impersonally and ends intimately. There is a certain humility in that. The visible world arrives not because reality has been packaged for human convenience, but because our bodies have evolved to exploit a stream of physical events already taking place. The photon does not exist for you. The sun does not shine for your retina. Reflection, scattering, and emission are not private performances. They are ordinary physical processes. You happen to be a creature whose survival and experience depend on catching some of them and turning them into sight. That transformation is marvelous, but it begins with a world doing what it does whether anyone is watching or not. Even so, the very fact that you can watch at all depends on astonishing sensitivity. The eye can respond to extremely low levels of light under favourable conditions. That means some visual experiences begin with very few photons arriving from a dim source or a darkened scene. At the brighter end, daylight floods the system with a torrent that must be managed rather than begged for. Vision spans an enormous range, and the photon journey changes in feel across those conditions. At noon, surfaces throw back enough light to make the world crisp and confident. At dusk, fewer photons arrive, contrasts soften, colours dull, and the limits of the system begin to show. The outside journey and the inside machinery are always negotiating. So when you say that you see something, it is worth remembering that a great many small travellers have already done their part. Some were born in a filament, some in a diode, some in the surface of a star. They crossed space, air, dust, and rooms. They struck matter and were altered by it. They carried onward the signatures of surfaces, shapes, edges, and colours. They reached your eye not as little messengers with written reports, but as physical events whose energies and directions encoded the state of the world outside you. This is the invisible journey that precedes every visible thing, and once those photons finally arrive at the entrance to the eye, the story does not become simpler. It becomes more selective, more mechanical, and in some ways even stranger, because the eye is not merely an opening. It is an instrument built to gather, focus, regulate, and deliver light with enough order that a living sheet of cells at the back can begin translating it into signals the nervous system understands. Most of the world does not shine. It only seems that way because it is very good at handling borrowed light. That is one of the quiet tricks behind ordinary vision. We look around and the room appears fully occupied by visible things. The blanket has a colour, the wall has a tone, the table seems to present itself, the page seems almost eager to be read. A tree outside the window appears green in daylight and dark against the evening sky. A face is visible at breakfast, a cup is visible on the sink, and a shelf of books waits to be judged by titles you have meant to remember. It all gives the impression that objects come preloaded with their own visibility, as though being seen were one of their native talents. But for most objects, that is not what is happening at all. They are not producing light for your benefit. They are borrowing it, modifying it, and sending some of it on its way. That borrowed quality is easy to miss because the process is so reliable. The sun rises or a lamp is switched on, and the world appears with such consistency that it feels built into the objects themselves. Yet, if all external light vanished, most familiar things would vanish with it, at least to sight. The chair would remain a chair, the mug would remain a mug, the page would still be sitting there with its ink and paper fibres and its slightly bent corner. But without light arriving from somewhere and interacting with those surfaces, nothing would be visible. In that sense, ordinary objects live visually on credit. They do not pay for their appearance out of their own luminous pocket. They use what falls upon them. The sun, of course, is the grand lender in the daytime. It floods the planet with light on a scale so extravagant that it becomes almost invisible as a fact. We notice bright mornings and cloudy afternoons, sunsets and shafts through leaves, but the sheer generosity of solar illumination is easy to take for granted. Sunlight spreads over streets, rooftops, oceans, fields, curtains, kitchen counters, and the side of your hand if it rests beside a window. That light is then taken up by the surfaces of the world, each surface responding according to its material structure. Some of the incoming light is absorbed, some is scattered, some is reflected in a more orderly way, some passes through. What comes back out toward your eyes is not the original light unchanged, but light edited by matter. That editing is the beginning of visibility. When light reaches an object, the object does not merely accept it or reject it in one dramatic gesture. It interacts with it selectively. The electric fields associated with the incoming light influence the charge particles in the material, especially electrons. Those charges respond according to the arrangement of atoms and molecules, the binding of electrons, the surface texture, the internal structure, and the wavelengths present in the light. Out of all that microscopic activity emerges what we describe in ordinary life with very simple words: bright, dark, shiny, dull, red, blue, transparent, opaque, soft-looking, harsh-looking, warm, cold, matte, glossy. Those are human terms for physical negotiations between light and matter. A white object is a useful place to start because it makes the borrowing especially obvious once you think about it. Why does white paper look white in ordinary daylight? Not because whiteness is glowing from within the paper like a tiny moral victory. It looks white because the paper reflects and scatters a broad range of visible wavelengths fairly evenly. Under sunlight, which contains a broad spread of visible light, the paper sends much of that spread back out, and to your eyes it appears white. But place that same paper under strongly coloured light and its appearance changes. Under deep red illumination it may look red-tinted. Under blue light it may look bluish. In dim orange evening light it no longer sends the same mixture toward you as it did at noon. The paper did not change its soul. The borrowed light changed, and the paper could only return what it had been given. The same logic applies to darker objects, though with a different balance. A black shirt appears black because it absorbs a great deal of the visible light that falls on it and returns comparatively little. It is still borrowing light, but it is not passing much of that borrowed wealth onward. The result is darkness to the eye. Yet black is not absolute absence in most everyday scenes. In bright sunlight, a black fabric still shows folds, edges, and texture, because some light is returned. Under softer lighting, details may disappear, because the already modest return falls closer to the limits of what the eye can easily separate. So even blackness in the visible world is often not pure void, but selective thrift. Colour, perhaps the most seductive part of appearance, is also borrowed. We say that a leaf is green, an apple is red, a lemon is yellow, and a navy sweater is not helping anyone trying to find it in low light. But from the physics side, colour is the consequence of selective reflection and absorption. The pigments and structures in a material interact with incoming light, so that some wavelengths are more strongly absorbed, while others are more likely to be scattered or reflected onward. A green leaf in sunlight is not manufacturing greenness as a kind of spiritual fragrance. It is sending more of the wavelengths that your visual system interprets as green, and keeping more of others to itself. Under a red lamp, that same leaf may look dark or strange because the illumination no longer provides the broad mix it had in daylight. You cannot reflect what never arrived. That line matters because it reminds us that visible colour depends on two things at once. First, the composition of the light source. Second, the selective behaviour of the object. Change either one and appearance can shift. This is why a shirt chosen in one shop can look unexpectedly different outdoors. It is why skin tones change under fluorescent lighting. It is why paint samples that seemed ideal under one lamp can become deeply disappointing in another room, usually after enough money has changed hands to make the discovery feel personal. The object is borrowing the light available and returning only certain parts of it. If the available light changes, the return changes too, The sun is especially effective as a lender because its visible output is broad and intense. Daylight offers enough range that many objects can reveal their selective preferences clearly. Pigments that absorb some wavelengths and return others behave vividly under solar illumination. Surface textures cast fine shadows and produce contrast. Transparent materials gleam and bend the light. White clouds blaze while dark soil keeps more light to itself. The whole visible world becomes legible because sunlight is rich enough to be filtered into countless differences. In weaker or narrower lighting, much of that visual richness contracts. A sodium street lamp, for example, can flatten colours dramatically because the illumination itself is limited. Suddenly the world is borrowing from a lender with fewer notes in circulation. It is also worth noticing that the sun is not the only lender, though it is the most familiar and important one for daytime life. A lamp, a screen, a candle, a fire, even moonlight can serve as the source from which objects borrow visibility. Moonlight is especially deceptive because it feels soft and independent, yet it too is borrowed. The moon does not shine in the way the sun does, it reflects sunlight. The night landscape under a full moon is therefore lit by a second-hand version of daylight, weakened and altered by reflection from the lunar surface, then scattered again by the surfaces of Earth, before some of it reaches your eyes. A moonlit field is, in a very literal sense, a scene illuminated by light that has already changed hands. Once you start thinking this way, the visible world becomes a network of borrowing and relending. Sunlight falls on a wall, the wall scatters some of it into the room. That scattered light then falls on the table returns some of it toward the cup. The cup sends some onward toward your eyes. A single visible object in a room is often lit not only by the direct source, but by light that has already visited other surfaces. This is why shadows are not perfectly black indoors, and why the world often feels gently filled with light, rather than cut into stark islands of brightness. Surfaces lend light to one another by scattering what they have borrowed. A room becomes visible because the traffic of illumination is shared. This also explains why the character of a room changes so much when the walls, floor, or furnishings change. A room painted white feels brighter not because whiteness is magical, though interior decorators have occasionally come close to implying this, but because white surfaces scatter a larger fraction of incoming visible light back into the space. Dark walls absorb more and relend less. A polished wooden floor sends light differently than a thick carpet. A mirror can redirect illumination across a room while preserving much more of its directional structure than a matte surface would. The physics is local and material, the mood is human, yet the two are tightly linked. Not all borrowing is diffuse. Some surfaces return light in a highly organised way. This is what makes a mirror so different from a wall. A matte wall sends incoming light out in many directions, because microscopic irregularities and material properties scatter it broadly. A mirror, by contrast, reflects light in a more orderly fashion. Rays arriving from a given direction are returned in a corresponding direction, preserving enough information about where they came from to form an image. That is why you do not merely see brightness in a mirror. You see structure, location, and the deeply unfair angle of your own face while you're trying to relax. The mirror is still borrowing light, but it lends it back with unusual discipline. Shiny objects fall somewhere along that spectrum. A polished spoon, a glazed ceramic mug, a still pond, or a lacquered table surface all return light with more directional order than a rough matte material. That is why highlights appear on them, and why reflections, even distorted ones, emerge. The object does not create those bright gleams from nothing. It redirects incoming light source by source. A bright highlight on a glossy apple is often an image of the lamp or the sun reflected toward you. In a way, shine is the visible signature of borrowing without too much scrambling. Texture complicates everything in interesting ways. A rough surface borrows light and then scatters it into many directions because its microscopic geometry sends different portions of incoming light along different outgoing paths. This is why chalk, cloth, Plaster, paper, and unpolished wood often look soft and even under normal illumination. The scattering is broad, and the surface does not preserve a sharp image of the source. A smoother surface preserves more order and appears glossier. Between those extremes lies a whole vocabulary of appearance, all rooted in the same basic fact. The object is handling borrowed light according to its physical structure. Transparent materials are borrowing too, though in a slightly different manner. A clean pane of glass appears nearly invisible at times because much of the incoming light passes through it rather than being strongly scattered back. Yet glass can still be seen because some light reflects from its surfaces, and because the transmitted light is bent and altered at boundaries. A drinking glass on a table becomes visible through its edges, highlights distortions and internal reflections. Water behaves similarly. It is visible not because it possesses a loud visual self-declaration, but because it changes the path of light, reflects some of it, transmits some of it, and sometimes scatters enough to reveal depth, ripples, or suspended material. Pure transparency is almost visual silence. We notice transparent things mainly where the borrowing is not perfectly silent. There is a temptation to think of this whole process as if light were paint being spread over surfaces. It is not a terrible intuition, but it misses the deeper point. The object is not simply coated in illumination. It is actively selecting from the light that reaches it and determining what returns. The visible world is therefore not a passive projection but an ongoing sorting operation. Every object around you is continuously acting as a filter, a reflector, an absorber, a scatterer, or some combination of all four. The world does not just receive light, it edits it. That editing becomes especially dramatic at the level of pigments and dyes. A blue fabric looks blue because the molecules involved absorb certain ranges of visible light more strongly and leave others to be reflected or scattered. Those absorptions are tied to electronic structure within the molecules themselves. Different arrangements allow different energies of light to be taken up. So colour, at bottom, has a quantum origin in the behaviour of electrons, even though by the time it reaches your eyes it feels like the most ordinary thing in the world. A child points to a blue toy and does not realise they're casually benefiting from selective absorption governed by the allowed energy states of complex molecules, which is probably for the best. Childhood is already busy enough. Natural objects often add another layer because colour can come not only from pigments, but from physical structure. The blue of some bird feathers, the shimmer of certain insect wings, and the iridescence on soap bubbles or oil films arise not just from simple pigment absorption, but from microstructures that manipulate light through interference and other wave effects. Here the object is still borrowing light, but the editing depends on geometry as much as chemistry. The result can shift with angle, giving rise to colours that seem to change as you move. These are lovely reminders that visible appearance is not a static property stored in a thing like a label in a drawer. It is an event produced by the encounter between light, material structure, and viewpoint. Even the sky participates in this borrowed system in a way that feels almost poetic without needing to become abstract about it. The blue dome above us in daylight is not a surface at all, yet it appears luminous because sunlight is scattered by molecules and small particles in the atmosphere. Some wavelengths are scattered more strongly than others, so light from across the sky reaches your eyes with a different balance than the direct light of the sun itself. The sky looks blue not because there is a giant painted ceiling overhead, but because air is borrowing sunlight and sending parts of it everywhere. At sunset, the geometry of the journey changes. More atmosphere lies along the path, and the balance shifts. The visible world is full of things that shine by courtesy. This borrowed quality also explains why visibility is relational. An object is never simply visible in isolation from lighting conditions. A white mug in bright daylight, in warm lamplight, in bluish screen glow, and in near darkness is not sending the same light toward your eyes each time. The material is constant, the returned light is not. What you experience depends on the combination of source and surface. That is why photographers obsess over light, Painters chase it, cinematographers schedule around it, and ordinary people discover at unfortunate moments that the living room paint does not resemble the tiny sample card they trusted in the shop. Lighting is not decoration added after visibility. It is one half of visibility. There is another subtle point hidden here. If objects borrow their appearance from light, then vision is never merely about the objects themselves. It is always about interactions. The visible scene in front of you is a report not only on what things are made of, but on how they are currently being illuminated. A red apple in sunlight and a red apple under a narrow red lamp may both look red, but the physical stories leading to that redness differ. In one case, the apple has filtered a broad spectrum. In the other, it may simply be reflecting the only visible light available. Two similar appearances can arise from different physical conditions. Vision is informed, but it is not omniscient. Still, under ordinary daylight, the system works beautifully. Sunlight arrives rich and broad. Objects sort it according to their materials. Surfaces scatter it in patterns that preserve enough information about shape and texture. Some of that edited light reaches your eye. The world becomes visible not because things have awakened into self-display, but because each surface participates in a constant exchange with illumination. The tree borrows the sun, the road borrows the sun, the curtains borrow the sun, the moon borrows the sun, and then the garden borrows from the moon. A lamp joins the economy after dusk, and the furniture begins borrowing from that instead. The visible world is a republic of second-hand light. Once that idea settles in, even the most familiar scene takes on a slightly different character. The cup on the bedside table is not just there waiting to be seen. It is actively returning selected portions of the light that reaches it. The page of a book is not inherently bright. It is bright because it lends back much of what it receives. The shadow behind a chair is not a positive substance, but a region where the borrowing is starved because direct illumination has been blocked. Every visible edge, tone, and highlight is the result of how well or poorly different parts of the scene are participating in the circulation of a light. And that circulation is exactly what the eye will soon have to manage. Because by the time light leaves an object and heads toward you, it is no longer raw illumination from the source alone. It is borrowed light carrying information about material, angle, texture, and shape. Somehow the eye must gather that returning light, sort it by direction, and deliver it to a sensitive surface without losing the structure that makes the world legible in the first place. To do that, the eye has to be far more than a simple opening. If all you needed for sight were a hole that allowed light in, then a pinprick in a sheet of paper would count as an adequate visual system, and although that can produce a very primitive image under the right conditions, it is hardly the sort of arrangement one wants when trying to read, walk through a room, recognize a face, or avoid stepping on something soft and regrettably alive in the dark. The eye is not just a gap in the head. It is an instrument. Not a perfect one, not a silent one, not one that arrives factory fresh and remains so forever, but an instrument all the same. It gathers light, bends it, filters it, regulates it, and delivers it to a living surface with enough order that the rest of the nervous system can begin the work of vision. In that sense, the eye is a small observatory made not of brass and stone and carefully polished telescope tubes, but of tissue, fluid, transparent layers, and cells that somehow manage to do optical engineering while remaining very much alive. That is part of what makes it so strange. We tend to think of instruments as rigid and external. Cameras sit in our hands, telescopes stand in domes, microscopes rest on benches. The eye, however, is both instrument and body. It is built from flesh, supplied with blood, kept wet by tears, adjusted by muscles, repaired imperfectly, and carried around in a soft skull by a creature that uses it for everything, from reading labels to contemplating distant stars, and occasionally staring into the fridge as if answers might present themselves. Yet despite all that biological messiness, the optical principles are very real and very exact. It helps to begin with a basic task. The light coming from the world does not arrive at the front of the eye as a neat pre-packaged picture. It arrives as countless rays, or, if you prefer, as a structured flow of photons travelling from many points in the scene in many directions. For an image to form, that incoming light must be sorted so that light from one point in the world ends up affecting one region of the light-sensitive surface at the back of the eye, while light from neighbouring points ends up affecting neighbouring regions. Without that sorting, the visual world would collapse into a general wash of brightness. So the first job of the eye is optical organisation. It must take the borrowed light of the world and arrange it into an image. The first major surface that helps do this is the cornea. This is the clear curved layer at the very front of the eye, the part through which incoming light first passes. Because the cornea sits at a boundary between air and the denser materials of the eye, it bends light strongly. This bending, which we call refraction, happens because light changes speed when it enters a new medium. It does not change speed reluctantly or after a polite discussion. It changes because the electromagnetic wave interacts differently with the material it is passing through, and that change in speed alters the direction of travel when the light meets the boundary at an angle. The curved shape of the cornea means that rays entering near different parts of its surface are bent in a coordinated way, beginning the process of bringing light from the outside world to focus. This is one of those quiet pieces of physics that disappears into familiarity. You do not usually wake up thinking about the refractive power of your cornea, unless perhaps you have slept in contact lenses and are now reconsidering several life choices. But the cornea does a large share of the focusing work. It is not just a protective window, it is an optical element, and an important one. If its shape changes too much, if its clarity is lost, or if its surface is irregular, vision is affected immediately because the very first stage of image formation has been disturbed. Behind the cornea lies a fluid-filled space. Light passes through this as well, then approaches one of the more visibly expressive parts of the eye, the iris. The iris is the coloured ring people notice when they look closely at one another, blue or brown or green or somewhere in the complicated territory between. Its visual charm, however, is not its main job. The iris is a muscular structure that controls the size of the pupil, the dark opening at its centre. That opening is not itself a little black object. It looks dark because you are seeing into the interior of the eye, where most incoming light is absorbed rather than reflected back out. The pupil is a gateway, and the iris adjusts its width depending on conditions. In bright light, the pupil becomes smaller. In dim light, it enlarges. This does not focus the image. That is a common confusion. What it does is regulate how much light enters. In a bright environment, too much incoming light could overwhelm the light-sensitive cells further back, reduce contrast, and generally make the whole system less manageable. In dim conditions, admitting more light improves the chances that enough photons will reach the retina to support vision. The iris therefore acts a little like the adjustable opening of a camera, though the eye is not simply a camera and the comparison can mislead if stretched too far. Still, the basic idea is sound. There must be some control over intake. Without it, the eye would be a poor instrument in a world where illumination changes constantly. The pupil has another optical effect as well. A smaller opening can improve image sharpness by reducing the range of angles from which light enters, much as narrowing an opening in a simple optical system can reduce blur. That is one reason why bright conditions often feel visually crisp. It is not only that more light is available, the optical geometry is also being constrained in a helpful way. In low light, the enlarged pupil admits more photons, but it also allows more optical imperfections to matter. So dim vision is often not only noisier in the sense of receiving less light, but softer as well. The eye is always making compromises between brightness and sharpness, between sensitivity and precision. After passing through the pupil, light reaches the lens. This is the structure people often imagine does all the focusing by itself, perhaps because it carries the word lens, and seems to have inherited the public relations budget of the entire eye. It is indeed crucial, but it does not work alone. The lens is transparent, flexible, and positioned behind the iris. Unlike the cornea, which has a fixed shape, the lens can change shape. That ability allows the eye to adjust focus for different viewing distances in a process called accommodation. When you look at something nearby, the lens becomes more curved, increasing its refractive power. When you look far away, it flattens somewhat. This shifting is carried out by a set of muscles linked to the lens by fine supporting fibers. It is mechanical, continuous, and usually so effortless that you barely notice it happening. That effortlessness is another disguise. Focusing on a page, then on the room beyond it, then back to the page again feels immediate because the muscles of the eye and the elastic properties of the lens handle the adjustment automatically. Yet what is taking place is a careful optical recalibration. The eye must alter how strongly incoming light is bent so that an image of the object of interest falls properly on the retina. If the focus lands in front of the retina or behind it, the image is blurred. Much of ordinary visual life is therefore an exercise in keeping the world optically honest by shifting focus as needed. This ability changes with age. The lens gradually becomes less flexible over time, making it harder to accommodate for near objects. That is why reading small text at close range becomes less friendly for many people as the years pass, and why menus in low light begin to inspire a very particular kind of arm extension. The physics has not changed. The instrument has aged. A less flexible lens can no longer alter its shape as easily, so the eye loses some of its ability to focus nearby scenes sharply without assistance. Once light has passed through the lens, it travels through the main interior chamber of the eye, which is filled with a clear gel-like substance. Then, at the back of the eye, it reaches the retina. This is the light-sensitive layer where the optical part of the story begins to hand things over to the biological and electrical part. But before we follow that transition, it is worth lingering on what the optics have accomplished. The eye has taken light from the outside world and formed an image on the retina. Not a mental image, not yet. A physical image. Different points in the scene correspond to different locations on that retinal surface. Bright regions in the world create stronger stimulation in some places, darker regions in others. Edges, patterns, shapes, and movement all have physical correlates in the distribution of light across the retina. The eye has effectively built a temporary map of the outside world out of focused illumination. There is a famous detail here that people enjoy because it sounds delightfully unsettling. The image formed on the retina is upside down and reversed from left to right relative to the scene outside. This is a straightforward consequence of how lenses form images. Rays from the upper part of the scene are bent downward onto the retina, while rays from the lower part are bent upward. Likewise for left and right. Now, this often gets presented as though the brain then flips the image back the right way, as if somewhere in the head there were a little projectionist rotating slides into place. That is not a very accurate picture. Your brain is not looking at the retinal image the way a person looks at a photograph. Rather, the retina and the rest of the visual system are organized so that the pattern of stimulation corresponds systematically to the outside world. Up and down, left and right, are part of the interpreted structure of experience, not labels pasted onto a retinal postcard. Still, the upside-down image is a useful reminder that what feels immediate and natural in conscious sight depends on surprisingly indirect physical arrangements. The eye, though admirable, is not optically perfect. No natural instrument built from living tissue was likely to be. There are small imperfections in focusing, slight aberrations, variability in shape, scattering within the media, and changes across the field of view. Light entering near the edges of a lens system does not always behave exactly like light near the centre. Different wavelengths can be bent slightly differently. Surfaces are not mathematically flawless. Fluids are not perfectly neutral. Yet the system works extremely well under ordinary conditions because the imperfections are limited, the brain is adaptable, and the retina is not passively recording in the way a laboratory sensor might. The entire visual system is built to extract useful structure, not to satisfy a physicist who has brought unreasonable standards to a biological setting. That said, the eye does borrow some strategies familiar from optics more generally. It uses curvature to focus light. It regulates aperture. It relies on transparency where transparency matters. It keeps its sensitive surface at a suitable distance from the refracting elements. In very broad terms, it behaves like an imaging system, but it is a living one, and that changes the atmosphere of the whole thing. The eye is moist. It is nourished. It heals to a degree. It is moved continuously by muscles that aim it. It is protected by lids that blink, spreading tears across the cornea to maintain clarity and comfort. Even the tear film over the surface of the eye plays an optical role, smoothing the front surface and helping preserve image quality. A dry or disrupted surface degrades vision because the very first refracting interface becomes less even. So one could say, without being too melodramatic, that blinking is part of your optical maintenance routine. The eye is also never truly still while you are awake. Small movements constantly shift its direction. Some are quick jumps from one point to another, others are slower tracking motions as you follow something moving. Tiny involuntary motions continue even when you think you are fixating on one spot. These movements are not flaws to be ironed out. They are part of how this system works. They allow different parts of the scene to be brought onto the most sensitive central region of the retina. They prevent visual fading that can occur when stimulation is held too perfectly constant. They help gather detail from the world piece by piece, with the impression of a stable scene emerging from many brief samplings. The eye as observatory is therefore not a fixed telescope bolted to a mount. It is an instrument that scans. And what a curious scanning strategy it is. Only a small central region of the retina provides the sharpest detail and finest colour discrimination, so the eye must point that region toward what matters moment by moment. Reading is a dance of brief jumps and pauses. Looking around a room is a sequence of selections. Even recognizing a face depends on moving the eyes so that different features are examined with sufficient resolution. Yet subjectively, the world feels as though it is all present at once in equal clarity. That is one of the clever illusions of normal sight. The eye gathers detail selectively, and the brain knits that selective sampling into a coherent scene. The structures of the eye also do a decent job of suppressing stray light and preserving contrast. The interior is not built to behave like a glittering little ballroom. It is arranged to absorb light that should not bounce around confusingly once it has entered. If too much internal reflection occurred, images would wash out. Contrast would suffer. So the observatory has darkened walls where darkening helps, transparent materials where transparency matters, and a geometry designed not just to admit light, but to discipline it. Still, all the careful focusing in the world would be meaningless without a sensitive surface waiting at the back. The retina is where the incoming light finally meets cells capable of responding to it. This is the moment the eye stops being merely an optical device and becomes the entrance to neural processing. Yet even here the design remains a little odd. In vertebrate eyes, the light must pass through several layers of cells before reaching the photoreceptors that actually detect it. That arrangement has inspired much muttering among those who would prefer nature to have consulted a cleaner blueprint, and yet it works remarkably well. Biological history is full of solutions that would never win a design contest and still manage to keep entire species going quite effectively. What matters for now is that the eye has delivered the world to the retina in a physically organized form. Borrowed light from objects has been gathered by the cornea, admitted through the pupil, adjusted by the lens, and focused onto a living surface. The cup, the wall, the face, the page, the moon, the branch outside the window, each has been reduced to a pattern of light across that inner layer. Not reduced in the dismissive sense, but translated into a form the body can work with. The observatory has done its part. It has received the sky, the room, and the borrowed light of ordinary things, and it has laid them out inside the eye with astonishing care. But focused light is still only light. However elegant the optics may be, seeing cannot truly begin until those photons are absorbed by specialized molecules, until physical energy becomes a cellular event, and until illumination stops being merely an image on tissue and starts becoming electricity in the language of the nervous system. That transformation begins at the retina, and it begins in a way that is stranger than most people expect. If you were inventing a visual system from scratch, you might imagine that light enters the eye, lands on a row of sensitive cells, excites them, and makes them fire more strongly. More light in, more electrical activity out. That sounds clean, logical, and exactly the sort of thing biology might have done if it were under strict supervision. But the actual arrangement is less obvious and far more interesting. The cells that first detect light do not respond by becoming more electrically active in the simple sense. In one of the more surprising choices in ordinary physiology, light causes them to reduce an ongoing electrical signal that is already there in darkness. Vision begins not with a cell shouting louder because light arrived, but with a cell changing its steady behavior because a photon has interfered with the routine. To understand why, it helps to picture the retina not as a flat screen waiting passively for the world to project itself, but as living tissue packed with specialized cells. At the deepest level for our purposes are the photoreceptors, the cells that actually absorb light. There are two broad kinds. Rods are extremely sensitive and are most useful in dim conditions, though they do not support rich color vision. Cones are less sensitive in low light but are essential for daylight vision, fine detail, and color discrimination. Between them they allow human sight to operate across an enormous range of brightness, from starlit scenes where the world becomes sparse and quiet to bright midday conditions where every edge seems to announce itself. Each of these photoreceptors is a real cell, with membranes, internal chemistry, and a carefully maintained electrical state. They are not tiny cameras or little bits of film. They are living devices that use molecules to catch photons and then turn that caught energy into a change in electrical behavior. That turning is what people mean by phototransduction, though the word can sound more intimidating than the process really is. It simply means converting light into an electrical signal the nervous system can use. The key event happens in special molecules inside the photoreceptors. These molecules include a light-sensitive component that can change shape when it absorbs a photon. That sounds innocent enough, but it is the crucial step. A photon arrives carrying a particular amount of energy. If that energy matches what the molecule can absorb, the molecule is altered. Not philosophically altered, physically altered. A component within it shifts its arrangement. A bent form becomes a straighter form. A small molecular change occurs that would be completely invisible to you from the outside, and yet will soon have consequences large enough to affect how brightly you experience the room. This is the moment where light becomes chemistry before it becomes electricity. The photon itself is gone in the sense that it has been absorbed. Its energy has been handed over to the molecule. That handover changes the shape of the light-sensitive pigment, and because shape matters enormously in biology, the altered molecule now behaves differently. It activates a partner protein nearby. That activated partner then influences other molecules in a cascade. The word cascade is appropriate because one absorbed photon does not merely cause one tiny isolated event. It begins a chain in which the first chain triggers another, which triggers another, amplifying the effect. Amplification is one of the great necessities here. A single photon is not a blinding event. The energy involved at the molecular level is tiny, yet under dark adapted conditions, rods can respond to astonishingly low levels of light. That sensitivity is possible because the system is built so that one photon can influence many downstream molecules. It is not unlike tipping the first tile in a line of standing pieces, except the biochemistry is more elegant and much less vulnerable to household cats. One change leads to many changes, and a very small physical event becomes large enough for the cell to register reliably. What is the cell doing electrically before light arrives? This is the part that tends to surprise people. In darkness, photoreceptors are already relatively active in a particular way. They maintain a steady inward flow of positively charged ions through channels in their outer membranes. These channels remain open because a chemical messenger inside the cell is present at a level that holds them open. As a result, the photoreceptor in darkness is kept in a relatively depolarized state compared with what happens in light. That word need not trouble us too much. It simply means the electrical difference across the cell membrane is being held at a level that supports continuous release of signaling molecules at the cell's output end. So darkness is not the absence of activity. Darkness is a maintained condition. The cell is doing something definite. It is holding channels open, allowing charge to flow, and continuously releasing neurotransmitter onto the next cells in the chain. The photoreceptor is, in effect, reporting darkness by maintaining a steady output. Then light arrives and interrupts that report. When the light-sensitive pigment absorbs a photon and the cascade begins, one of the main results is that the level of the internal messenger keeping those channels open starts to fall. As that messenger level drops, channels in the membrane close, fewer positive ions enter the cell, the electrical state shifts, the photoreceptor becomes more negative inside relative to before. In other words, light causes the cell to hyperpolarize. Again, the term is less important than the logic. Less inward positive charge means the cell changes its voltage. That voltage change then reduces the amount of neurotransmitter released at its output. This is the crucial inversion at the heart of photoreception. Light does not simply make the receptor pour out more signal, it reduces the receptor's ongoing dark release. A bright stimulus therefore produces a stronger reduction, while dimmer light produces a smaller one. The cell is effectively measuring light by how much it deviates from its dark condition. In a way, the baseline state of the photoreceptor is a prepared readiness in darkness, and photons push it away from that baseline. There is a certain practical elegance in this. By keeping a steady flow going in darkness, the system can respond both quickly and in graded fashion when light changes. The amount of neurotransmitter released by a photoreceptor is not merely on or off under many conditions. It can vary continuously with the amount of light absorbed. That makes the cell well suited to representing gradual differences in brightness. The world is not usually a simple alternation between total blackness and blinding white. It is a landscape of continuous variation, and the receptor's electrical behavior reflects that. The structure of the photoreceptor supports all of this. One end contains the light-catching machinery, packed into stacked membranes that greatly increase the area available for the pigments that absorb photons. More membrane means more pigment molecules, and more pigment molecules mean a higher chance that incoming light will be captured. This is especially important in rods, where sensitivity is everything. The other end of the cell communicates with downstream retinal neurons by releasing neurotransmitter. Between these ends lies the living machinery that sustains the cell, restores its chemical components, and keeps the whole process going continuously. Photoreceptors are not one-use traps. They must absorb photons again and again over a lifetime, recover after each event, and adapt across conditions ranging from near darkness to bright daylight. Recovery matters because the light-sensitive pigment cannot remain in its activated state forever. After it has changed shape and triggered the cascade, it must be reset through a series of biochemical steps. Otherwise, the receptor would remain in its altered condition and lose the ability to report new light accurately. This resetting takes time, and it is one reason why vision has temporal limits. The system can be very fast, but it is not instantaneous in the magical sense. Molecules need time to change, proteins need time to activate and deactivate, internal messenger levels need time to rise and fall, and neurotransmitter release needs time to adjust. The eye is swift enough for ordinary life, but it is still built from physical processes unfolding in real time. That timing becomes very noticeable when lighting conditions change dramatically. Walk from bright sunlight into a dim room, and you do not immediately see as well as you will a few minutes later. Part of that is because the pupil changes size, but pupil adjustment is only a small piece of the story. Much more important is adaptation inside the retina, especially in the photoreceptors. In bright light, many pigments have been activated and the biochemical machinery is operating in a different regime. Rods may be heavily affected and less useful. Cones handle bright conditions better but have different sensitivities. As you move into dim light, the system gradually rebalances. Pigments regenerate. Internal messenger systems shift. Sensitivity increases. The world slowly reappears in low light, first coarsely and then with greater confidence. Dark adaptation is not psychological. It is biochemical and electrical. The reverse is true when you step suddenly into bright light. The system is overwhelmed at first because far more photons are arriving than it was recently prepared to manage. Receptors respond strongly, downstream circuits saturate, and vision can feel washed out or painful for a moment. Then adaptation mechanisms reduce sensitivity. This ability to adapt is one of the great achievements of the visual system. The range of light intensities in the natural world is enormous, far greater than any single fixed detector could handle gracefully. Photoreceptors therefore do not merely detect light. They continually adjust their operating conditions to remain useful. There is also the matter of noise, which sounds like an odd thing to bring into a discussion of sight, until one remembers that biology is not running inside a silent laboratory. Molecules can change state randomly. Cells have spontaneous activity. Thermal energy can nudge events along even in darkness. If the system were sensitive enough to treat every tiny random event as meaningful light, vision in the dark would be a constant hallucination of false brightness. So sensitivity has to be balanced against reliability. Rods are incredibly sensitive, but the retinal circuitry downstream is arranged to help distinguish real signals from random fluctuations. Even so, at the limits of vision, certainty becomes delicate. Dim scenes are not only less detailed because fewer photons arrive, they are also closer to the noise floor of the system. Cones work somewhat differently from rods, though the basic principle of light causing a molecular change that alters electrical behavior remains the same. Cones are less sensitive individually, but they respond more quickly, recover faster, and come in different classes with different pigment sensitivities. That difference in spectral sensitivity will matter later when colour enters the story properly. For now, it is enough to say that cones are the photoreceptors that let us see detail and colour in brighter conditions, while rods support highly sensitive vision when light is scarce. Both convert photons into graded electrical changes through related biochemical logic. One of the most fascinating consequences of this arrangement is that brightness is not measured in the retina by a single grand meter reading the world like a room thermostat. It is measured locally, receptor by receptor, through countless tiny changes in electrical state produced by absorbed photons. Every point in the image cast on the retina corresponds to many receptors responding according to how much light has reached them and what kind of light it was. A bright patch in the world produces a stronger reduction in dark current in some receptors than a dim patch. A shadow produces less change. Fine patterns produce differences across neighbouring cells. The image is no longer just an optical distribution of light. It is becoming a pattern of cellular activity. Still, it is not yet the kind of spiking electrical language many people imagine when they hear the words nerve signal. Photoreceptors communicate in a graded way. More light can mean a larger change in membrane potential and a correspondingly larger change in neurotransmitter release. This is a subtle signal, more like turning a tap than flipping a switch. The next layers of retinal cells will interpret that graded input and begin extracting more structured information from it. Some of those downstream cells will eventually generate the rapid all-or-nothing impulses that travel along the optic nerve to the brain, but the photoreceptors themselves are handling the first stage with more nuance. The chemistry that links photon absorption to channel closure is also a fine example of how evolution makes use of indirect routes when direct ones would be too weak or inflexible. A photon could in principle change a molecule, and perhaps alter an ion channel directly, but the cascade provides gain, control, and opportunities for adjustment. It allows a single event to have a measurable effect. It allows the system to tune sensitivity. It allows adaptation to different ambient conditions. In short, it makes the receptor more useful than a simple one-step trap would be. Biology loves cascades for this reason. They are excellent ways of turning small inputs into regulated outputs. There is an irony here that is easy to appreciate once noticed. The world feels brightly, continuously visible, yet the actual physical trigger in the receptor is a molecular event at a tiny scale. A single photon is absorbed by a pigment molecule buried in the membrane of a cell in the back of the eye. That tiny interaction changes shape, activates proteins, closes channels, alters voltage, reduces transmitter release, and thereby contributes to your experience of a lamp, a face, a line of print, or the edge of a curtain moving in a draft. Sight feels broad and immediate because immense numbers of these events are happening across the retina all the time, but each one begins at the scale of molecules. And because it begins at the scale of molecules, it is vulnerable to the practical realities of molecules. Pigments bleach under strong light and must be regenerated. Nutrients must be supplied. Waste must be cleared. The retina has a supporting tissue that helps maintain the photoreceptors, recycles important components, and absorbs stray light. Without that support, the receptors would not remain reliable. The transformation of light into electricity may sound like a clean single event, but in living tissue it depends on a large amount of background maintenance. The observatory works because someone is constantly cleaning the lenses, tending the machinery, and replacing worn parts, except in this case the someone is a network of biological support processes rather than a patient caretaker in sensible shoes. What the photoreceptor has produced by this stage is not an image in the conscious sense, and not a decision about what is being seen. It has produced a local electrical report about light capture. More precisely, it has changed its release of neurotransmitter according to how many photons it has absorbed, and how its adaptation state currently stands. This output is then handed to the next retinal cells, which do something extremely important. They compare, separate, amplify, suppress, and reorganize the information. The retina is not a passive sheet of detectors forwarding raw data. It begins processing immediately. Some downstream cells respond to increases in light. Others respond to decreases. Some emphasize contrast. Some begin integrating signals from multiple receptors. The moment light becomes electricity is therefore not the end of a conversion. It is the opening move in a conversation. That conversation is easy to overlook because the word retina sounds so flat and simple, almost like the name of a surface rather than a layered piece of neural tissue. But once photons have been absorbed and the receptors have changed their electrical state, the retina has work to do with that information before anything leaves the eye. Signals must pass through intermediate cells, split into different channels, and be organized into forms useful for later vision. By the time the message leaves the retina, it is no longer just a record of local light levels. It has already been edited by the retina's own internal logic, which is where the quiet business of seeing starts to become less like recording and more like interpretation. What follows is where the retina stops behaving like a simple receiving surface and starts acting more like a piece of living neural tissue with opinions. Light has already been absorbed. Photoreceptors have already changed their electrical state. Molecules have shifted shape, channels have closed, and the first conversion from light into electrical change has taken place. If the eye were only an optical instrument, that might be the end of its role. It would form an image and pass the result along, rather like a well-behaved delivery service. But the retina is not content with that arrangement. It does not merely collect signals from rods and cones and send them onward unchanged. It compares them, reshapes them, suppresses some, sharpens others, and sorts the incoming flow into several different kinds of information before anything ever reaches the brain. This is one of the most important facts about vision, and one of the least intuitive. People often talk as though the brain does the seeing and the eye just sends the picture. That is only partly true. The brain does indeed contribute enormously, but the retina is already part of the brain in a developmental and functional sense. It is neural tissue, not just a screen. By the time signals leave the eye through the optic nerve, they have already been processed by a layered network of cells, carrying on a constant internal exchange. The scene in front of you is not forwarded as a raw photograph. It is edited on site. To understand why that editing is necessary, imagine what the photoreceptors alone are actually reporting. Each rod or cone responds according to the amount of light it absorbs. That is useful, but on its own it is not enough to build a stable, informative view of the world. The absolute amount of light falling on a surface can vary wildly depending on time of day, shadows, weather, lamps, reflections, and viewpoint. If the visual system relied only on raw light levels at each point, it would constantly struggle to distinguish whether a region was truly different in the world or merely differently lit. A white page in shade can return less light than a dark object in direct sunlight. Yet we do not usually confuse the two. Part of the reason is that the retina begins the work of comparison immediately. It cares not only about how much light each receptor is reporting, but about how that report differs from the reports nearby. The first major cells to receive input from photoreceptors are bipolar cells. The name sounds slightly like a diagnosis made by a Victorian naturalist, but it is simply descriptive. These cells form a bridge between photoreceptors and later retinal neurons. What matters is that they do not all respond in the same way. Some bipolar cells are activated when light in a certain region increases, others are activated when light decreases. This is one of the fundamental divisions in retinal signaling. The system separates increments from decrements. It creates pathways for lights turning on and for lights turning off, for brightening and darkening, for the appearance of a lighter patch and the appearance of a shadow edge. That split begins because the reduction of neurotransmitter release from photoreceptors in light is interpreted differently by different bipolar cells. One class is wired so that less transmitter from the photoreceptor means more activity in the bipolar cell. Another class is wired so that less transmitter means less activity. The result is that the retina produces separate channels, often referred to as on and off pathways. These names are wonderfully plain for something so important. They mean that the visual system does not just encode brightness as a single number rising and falling everywhere. It represents increases and decreases in separate streams. This turns out to be enormously useful for detecting edges, changes, contrast, and motion. It also tells us something about how vision is built. The retina is not asking only how much light is there. It is asking whether things are getting lighter or darker, relative to a given baseline and relative to neighbouring space. A white object against a grey background and a grey object against a black background may produce similar absolute values in some places, but the contrasts differ, and the retina is particularly interested in those differences. Much of what makes the world legible is contrast. Edges are contrast. Text on a page is contrast. The outline of a face against the room behind it is contrast. The rim of a cup, the fold in a blanket, the border between shadow and sunlight, all of it depends on local differences more than on absolute light alone. This is where horizontal cells enter the conversation. These cells spread sideways across the retina, linking signals from neighbouring photoreceptors and influencing how bipolar cells interpret input. Their role is not to carry the main signal straight onward, but to provide lateral interaction. That side-to-side communication is what allows the retina to compare one region with its surroundings. A photoreceptor does not exist in total social isolation, nobly reporting its own little patch of the world and refusing all gossip. Its output is affected by context. Nearby regions matter. Horizontal cells help create that context. The result is something known as center-surround organization, and this is one of the retina's cleverest strategies. Instead of responding simply to a spot of light in a uniform way, many retinal neurons are arranged so that light in the center of their receptive area has one effect. while light in the surrounding area has the opposite effect. A cell might be excited by light in the centre and inhibited by light in the surround, or the other way around. These are not abstract labels, they are practical comparisons built into the wiring. The cell is effectively asking whether the centre differs from the surround. If the centre is brighter than the neighbourhood, that is interesting. If the surround is brighter than the centre, that is also interesting. If everything is evenly illuminated, the difference is less informative. This organisation makes the retina especially good at detecting edges and boundaries. Suppose light falls evenly across a broad uniform surface. Many cells with centre-surround receptive fields will receive similar stimulation in centre and surround, and their responses may partly cancel. But at an edge, where one side is brighter and the other darker, the balance is disturbed. Suddenly the difference between centre and surround becomes strong, and the cell responds robustly. In this way, the retina emphasizes change across space. It highlights transitions. It marks where one thing ends and another begins. A system that did not do this would be far less effective at extracting useful structure from the world. This is closely related to what is often called lateral inhibition, a phrase that sounds far more sinister than it needs to. It simply refers to the fact that activity in one region can suppress the influence of neighbouring regions through side connections in the retinal network. This sharpening makes bright areas appear more distinct next to darker ones and helps preserve edges. It is also responsible for some classic visual illusions in which gradients or patches appear lighter or darker than they physically are because the retinal circuitry is exaggerating local contrast. In those illusions, the retina is not malfunctioning. It is doing what it usually does well, emphasizing differences in a world where differences often matter more than absolute values. The occasional illusion is the price of a strategy that works brilliantly most of the time. Bipolar cells and horizontal cells are only part of the story. Deeper in the retinal circuitry, amacrine cells join the discussion, and they bring a whole new level of complication. These cells are astonishingly varied. Some help shape timing. Some influence motion sensitivity. Some contribute to the separation of on and off signals. Some regulate how ganglion cells respond depending on the recent history of stimulation. If horizontal cells are the early neighbours sharing side glances, amacrine cells are the busy intermediaries making sure the signal is not just spatially compared, but also temporally tuned. They help determine what counts as a change worth noticing, how transient or sustained a response should be, and how motion across the retina should be represented. Motion is a good example of why raw transmission would not be enough. If an object moves across your field of view, the pattern of light on the retina changes over time. A purely static encoding of brightness at each point would require later stages to do all the work of figuring out that something moved. The retina begins assisting much earlier. Certain circuits are especially sensitive to movement in particular directions or to changes that occur quickly. This helps the visual system respond to moving objects with speed. From an evolutionary point of view, that is not difficult to justify. A creature that notices movement promptly has practical advantages, whether the moving thing is food, danger, or another member of its species behaving in a way that deserves immediate attention. All of this processing converges onto ganglion cells, whose long fibres form the optic nerve. Ganglion cells are the final output neurons of the retina. They are the cells whose signals actually leave the eye and travel toward the brain. By the time a ganglion cell fires, the input it receives has already been shaped by photoreceptors, bipolar cells, horizontal cells, and often amacrine cells. It is therefore not carrying a raw report of photon counts. It is carrying a process statement about contrast, change, timing, or some other feature extracted by the retinal network. Ganglion cells are not all identical either. Some are better suited to fine spatial detail. Others are better at detecting broad, fast changes. Some are involved in colour-related comparisons. Others are more concerned with brightness or motion. Different classes send different streams of information forward in parallel. This is another important point. The retina does not compress the scene into a single uniform code. It splits vision into multiple channels at the very start. The brain receives not one message about the world, but many coordinated messages emphasizing different aspects of it. There is a trade-off hidden in this arrangement, and it appears clearly when we compare rods and cones. In the fovea, the central region of the retina responsible for the sharpest vision, cone signals are passed along with relatively little convergence. One cone may connect through a dedicated pathway that preserves fine detail. This is excellent for high acuity vision. It lets you read small text, inspect edges, and notice subtle patterns, but it is not maximally sensitive in dim light. In the peripheral retina, especially in rod pathways, many receptors may converge onto fewer downstream cells. This boosts sensitivity because weak signals from several rods can be pooled, but it sacrifices fine detail because individual contributions are no longer kept as separate. The retina is constantly balancing resolution against sensitivity. You can have exquisite detail with lower light gathering efficiency, or greater sensitivity with lower spatial precision. The system uses both strategies in different places and under different conditions. That is why a dim star at night can sometimes be seen more easily if you do not look directly at it. The fovea, rich in cones and optimized for detail, is not the most sensitive region in low light. Slightly off to the side, the rod-rich peripheral retina may detect the faint light better. It is a small, everyday example of retinal specialization quietly affecting experience. The eye feels like a single organ with a single mode of seeing, but the retina is more like a patchwork of strategies tuned for different jobs. The secret conversation in the retina is therefore not just about passing signals forward. It is about deciding what kind of signals should be passed forward and in what form. Uniform areas of illumination are downplayed. Differences are enhanced. Brightening and darkening are separated. Rapid changes may be emphasized over slow ones. Fine detail is preserved in some regions and sacrificed in others for the sake of sensitivity. Motion can be signaled early. Some pathways carry information with high spatial precision, others with faster timing. The retina is already organizing the world into useful categories before conscious sight has even had a chance to feel immediate. One of the most striking consequences of this is that the brain never receives a complete untouched image from the eye. That popular picture is simply wrong. What leaves the retina is already selective. Some information has been amplified, some has been suppressed, some has been averaged across neighboring receptors, some has been split into parallel channels that emphasize different features. The world you will eventually experience as stable and unified begins as several edited reports. This is not a flaw. It is the reason vision is efficient enough to work. It also explains why visual experience is not a perfect record of physical reality. The retina is built to extract what tends to matter. Contrast matters more than absolute light level. Change matters more than static uniformity. Edges matter. Movement matters. Relative differences matter. This is generally useful, but it means that certain arrangements of light can mislead the system. Under carefully chosen conditions, the retina will exaggerate or distort aspects of a scene because the circuitry is following its normal rules. A grey patch can appear lighter or darker depending on its surround. Stationary patterns can seem to shimmer. Boundaries can look sharper than the measured light profile really is. These are not failures of honesty. They are side effects of a strategy optimized for natural scenes rather than for passing philosophy exams. The temporal dimension is just as important as the spatial one. Retinal cells do not all respond for the same duration or with the same speed. Some respond strongly at the onset of a change and then quiet down, making them good at signaling sudden events. Others maintain activity as long as the stimulus remains. This means the retina is already separating transient from sustained information. A new object appearing in view may trigger a brisk response, while a steady surface may be represented differently over time. In effect, the retina is sensitive not only to what is where, but to what is changing and how quickly. The world is not frozen while you see it, and the retina is not pretending otherwise. Meanwhile, all of this is happening continuously across millions of cells, with incoming light patterns shifting because your eyes move, the scene changes, or both. Every glance across a room sets off fresh combinations of local comparison, contrast enhancement, timing adjustment, and parallel signaling. The retina is not waiting for grand visual moments. It is working all the time, whether you're reading, walking, looking at a face, or staring out of a window while supposedly thinking about something else. That silent labour is part of why sight feels so immediate. Enormous processing has already happened by the time you become aware of anything at all. There is also a certain humility in realizing that much of what feels like direct contact with the world is already the result of a negotiation inside the eye itself. The edge of a shadow looks clear because retinal circuitry helps sharpen it. A moving object catches your attention, partly because retinal pathways are tuned to changes over time. A letter on a page stands out because local contrasts have been emphasized. The retina is not composing poetry about the scene, it is doing practical work. But that practical work is what allows later stages to build the experience we casually call seeing. By now, the visual signal has become something very different from the original pattern of light that entered the eye. It began as borrowed photons returning from objects. It became a focused image on the retina. It became molecular change in photoreceptors, then graded electrical signals, then patterns of comparison and contrast through retinal circuits, and finally trains of impulses in ganglion cells heading toward the brain. What leaves through the optic nerve is already a set of curated messages about the scene. Among those messages is one that will matter a great deal for what comes next, because the retina is not only comparing brightness and contrast, it is also comparing the outputs of different kinds of cones, and that means some of its secret conversation is already about colour, not as a decorative extra, but as a structured difference in the light returning from the world. That comparison is where colour really begins, and it begins with a slight disappointment to anyone hoping that redness or blueness lives inside the world in a simple, permanent way. From the point of view of physics, the light arriving at the eye carries information about wavelength and intensity. From the point of view of the retina, the cones respond according to how sensitive they are to different parts of that incoming light. But from the point of view of your experience, what you get is colour, and colour is not the same thing as wavelength. That distinction matters more than it first appears. It means that the rich painted quality of the world is not lying openly on the surfaces of objects, waiting to be picked up whole. It is something your visual system constructs from a limited set of comparisons. This is why colour can feel both obvious and strangely slippery. Everyone knows what red is in daily life. A red mug is red. A traffic light turns red. A tomato is red unless it is being sold before it had any right to be. Yet when you try to pin down what red actually is in physical terms, the answer shifts. It is not simply one exact wavelength, because many different mixtures of wavelengths can produce an experience we still call red. It is not simply a property stored in the object, because the same object can look different under different illumination. It is not simply something in the light source either, because the same light can produce different colour experiences depending on surrounding context and the state of your visual system. Colour is one of those cases where the world provides the ingredients, but the finished product belongs to the nervous system. The first step is still firmly physical. Cones, unlike rods, come in different types with different sensitivities to wavelength. Human vision typically relies on 3 cone classes. One is most sensitive toward longer wavelengths, another toward middle wavelengths, and another toward shorter wavelengths. These are often loosely associated with red, green, and blue, though that simplification can be a bit misleading. The cones are not tiny red detectors, green detectors, and blue detectors in the childish paintbox sense. Each type responds across a broad range, and those ranges overlap heavily. A given wavelength of light can stimulate more than one cone type at once, just in different proportions. The visual system then uses the pattern of relative responses to infer colour. That relative part is crucial. A single cone by itself cannot tell you the colour of the light it has absorbed. It can only report how much it has been stimulated. A stronger response could mean more light at a preferred wavelength, or simply more total light of a less preferred kind. This is called the problem of univariance, though the name is less important than the idea. One receptor alone cannot separate wavelength from intensity. To determine colour, the system must compare different cone types. If one class responds strongly, another moderately, and another weakly, that pattern means something. A different pattern means something else. Colour begins as a ratio. This makes colour vision a remarkable feat of inference. The retina is not opening little drawers labelled red, green and blue and sorting photons neatly into them. It is measuring overlapping responses across cone populations and using those differences to build a colour signal. When light from a yellow surface reaches the eye, there is no tiny yellow essence floating in with it. Instead, the longer and middle wavelength sensitive cones may be stimulated more strongly than the shorter wavelength sensitive ones, and the pattern of those responses contributes to the experience of yellow. Another combination of physical wavelengths might produce a very similar pattern in the cones, and therefore look the same, even if the light itself is physically different. This is one of the more unsettling and useful truths in colour science. Different spectra can look identical to us if they drive the three cone classes in the same overall way. That is why a colour on a screen can resemble a colour on a painted wall, even though the physical light coming from each is not remotely the same in detail. A screen often creates many visible colours by combining different amounts of a few primary emissions. A painted wall reflects a broad and irregular slice of whatever light falls upon it. The resulting light entering your eye can be very different as a physical spectrum and still produce nearly the same cone responses. Your visual system calls them the same colour because from its point of view they effectively are the same. This is not carelessness. It is the unavoidable consequence of compressing the enormous complexity of possible light spectra into 3 cone channels. So colour is already a kind of reduction. The world contains many possible distributions of light across wavelength. Your eye samples that complexity through 3 broad filters. The brain then builds colour experience from the comparisons between them. There is great efficiency in this, but also limitation. It means that colour as we know it is not the full, physical story of light. It is a biologically useful summary. Once the cone's signals leave their receptors, the story becomes even more interesting, because the visual system does not keep them only as 3 separate streams. It begins recombining them into opponent channels. One channel roughly compares longer wavelength sensitive cones against middle wavelength sensitive cones. Another compares the combined output of those two against shorter wavelength sensitive cones. A third carries information related more to overall brightness than hue. This opponent arrangement helps explain several features of human colour experience that would otherwise seem odd. We do not typically perceive a colour as both reddish and greenish in the same place at the same time, or both bluish and yellowish in the same straightforward way. That is because the system is not representing colour as an unrestricted mixture of labels. It is representing it through comparisons, through oppositions. This opponent organisation also helps explain after images. If you stare at a strongly coloured object for a while, and then look at a neutral surface, you may see a ghostly image in a complementary colour. A red patch may leave behind a greenish after image. A blue patch may yield a yellowish one. That happens because the visual pathways involved in coding colour adapt over time. Prolonged stimulation shifts their balance, so when the original stimulus is removed, the neutral surface is processed through a temporarily biased system. The after image feels like a strange trick, but it is really a glimpse of how the comparison machinery works. It also reveals something deeper. Colour is not passively read off the world. It is actively maintained and adjusted by the visual system. The same is true of colour constancy, which is one of the quiet miracles of normal seeing. A white sheet of paper looks roughly white at noon, in shade, and under many indoor lights, even though the actual light reaching your eyes from the paper can be very different in each case. Physically, the spectrum reflected from that paper changes with the illumination, yet you often still experience it as the same white paper. This means the visual system is making an implicit correction. It is not merely reporting the raw incoming light, it is estimating, in a rough and usually effective way, the likely illumination and the likely reflectance of the object. It is trying to separate what belongs to the light source from what belongs to the surface. That is a difficult problem, and the system solves it impressively well most of the time. You rarely walk around feeling that the whole world changes colour every time a cloud passes. Instead, colours appear fairly stable across changing conditions. A banana still looks yellow in a kitchen and in a garden. A dark blue coat remains dark blue even under warm indoor lamps, though it may shift slightly. This stability is not because the incoming light is stable. It is because your visual system is good at discounting the illuminant, as vision scientists like to say. In simpler terms, it tries to look past the colour of the light source and recover the colour of the object. Sometimes it does this so aggressively that it produces famous disagreements. A photograph taken under ambiguous lighting can cause some people to interpret the illumination one way and others another way, leading to dramatically different reports of the same dress, shoe, or other unexpectedly controversial object. These episodes briefly remind the public that colour is an interpretation, not a direct reading. Under ordinary conditions, the interpretation is so consistent and so shared that we forget it is happening. But when the available cues are poor, the mind's role becomes impossible to ignore. This is also why colour can be context-dependent in subtler ways. A grey square may look slightly bluish against one background and slightly yellowish against another. The same patch can seem lighter or darker, richer or duller, warmer or cooler, depending on its neighbours. The visual system is not merely measuring local wavelength content in isolation. It is comparing regions, estimating illumination, adjusting for surroundings, and trying to produce a useful and stable account of the scene. Colour is therefore relational. It depends on what else is around, on what came before, on how adapted the eye is, and on what assumptions the system is making about the world. There is a nice irony in the fact that one of the most vivid parts of experience is also one of the most clearly constructed. Colour feels immediate, it feels attached to things, it feels as though it simply belongs there, sitting on the surfaces of apples and leaves and curtains and clouds. But physically, what belongs there are materials with certain reflectance properties under certain illuminations. Experientially, what appears there is colour. The two are connected, but they are not identical. Purple is a particularly good example of this distinction. People often assume that every colour corresponds neatly to one place in the visible spectrum. Some do, in the sense that a narrow band of wavelengths can produce experiences we call red, green, or blue. But purple, in the ordinary sense, is not produced by a single narrow spectral band in the same way. It arises when shorter and longer wavelengths stimulate the visual system in a pattern that the opponent channels interpret as a purplish hue. In other words, purple is a very real colour in experience, but it is not a simple one-step label for one spectral location. It is built by the system from comparisons. This tends to surprise people, perhaps because purple feels far too respectable to be so obviously invented. Even more ordinary colours are full of invention once you look closely enough. Brown, for example, is not just dark orange in a simple paint chart sense. It is strongly dependent on context and relative brightness. A patch that looks orange in one setting may look brown in another if its luminance is lower, relative to surrounding regions. Pink depends on brightness and context too. Metallic colours involve highlights and reflectance patterns that ordinary matte colours do not. Gold is not just yellow. Silver is not just grey. The visual system uses a combination of chromatic and brightness cues, along with assumptions about surface reflectance and illumination, to create these categories. The visible world is more than a list of wavelengths with names beside them. At night, colour begins to retreat, and that too tells us something important. In very dim light, rods dominate vision because they are more sensitive than cones. But rods do not support colour discrimination in the way cones do. As illumination falls, the world loses some of its chromatic richness. Reds darken disproportionately, blues may seem relatively more present, and the whole scene becomes quieter in colour. A garden at dusk is not the same chromatic place it was at noon. This is not because the flowers have become emotionally reserved. It is because the receptors supporting vision have changed. The mind's invention of colour depends on having enough cone input to work with. That shift is also one reason why dim scenes can feel flatter or less certain. Colour is one of the many cues the visual system uses to separate surfaces and identify materials. When it fades, the world becomes less richly specified. Shapes may remain, motion may remain, brightness differences remain. But some of the categorical ease of recognition weakens. A dark blue sock and a black one become less distinguishable, which has caused more practical household confusion than science textbooks usually acknowledge. Not everyone experiences colour in the same way either, because the biological hardware can differ. If one class of cone pigment is absent or altered, colour comparisons change. This is the basis of common forms of colour vision deficiency. A person missing one type of cone is not living in a world without all colour, despite how such conditions are often described in oversimplified terms. More often, the world still has colour, but certain distinctions collapse or become much harder to make because the comparison space has changed. Reds and greens may become less separable. Some hues that others distinguish clearly may appear much more similar. The world is still visible, detailed, and meaningful, but its chromatic structure is organised differently. This is a useful reminder that colour is not a simple public fact independent of the observer. It is a relation between the physical light available and the sensory machinery receiving it. Change the machinery and the colour world changes. Many animals do not share our particular three-cone arrangement. Some have fewer cone types, and therefore a more limited colour space. Others have more and may discriminate differences we cannot imagine directly. Birds, insects, and other species can detect parts of the spectrum outside human vision altogether. The world they see is not merely our world plus a tint. It is organised by different receptor comparisons and therefore supports different colour experiences or colour-like distinctions. Human colour is not the universal answer, it is our answer. Yet within its limits it is extraordinarily effective. Colour helps us identify ripe fruit, healthy foliage, blood flow in skin, signals in the environment, materials, stains, bruises, flames, weather changes, and countless culturally important objects, including clothing choices that seemed wise in the shop, and less so by morning light. It is both practical and expressive. It carries information and also shapes mood, memory, preference, and art. But underneath all of that lies the same basic fact. The eye receives light. The cones compare wavelength content through overlapping sensitivities. Retinal and later neural circuits build opponent channels and adjust for context. The result is colour experience. Calling it the mind's invention does not mean it is fake in the dismissive sense. It means it is constructed, which is different. Temperature is constructed by the nervous system from physical interactions with heat. Sound is constructed from pressure waves entering the ear. Colour is constructed from light. But none of these are arbitrary fantasies. They are lawful interpretations that organisms use to navigate the world. Colour is real as an experience and deeply useful as a perceptual category. It is simply not a paint already spread on the universe before minds arrive. This becomes even clearer when we consider how quickly colour can be revised by the system. Put a grey card under a coloured light, and it may look tinted. Surround that same card with different neighbouring colours and its appearance shifts. Adapt to a strong hue and the world temporarily rebalances around it. Change illumination and constancy mechanisms work to preserve object colours where possible. All of this is happening beneath awareness. You do not consciously compute cone ratios and opponent responses while looking at a lemon. You just see yellow. The construction is hidden because a hidden construction is usually the most convenient kind. The convenience, however, comes with some odd consequences. There are colours that can be named easily but not specified by one spectral line. There are physically different lights that look identical. There are stable object colours that persist despite changing illumination. There are illusions in which context changes appearance without changing local stimulus. There are afterimages, colour adaptation effects, and ambiguities that reveal the machinery behind the curtain. In other words, colour is both one of the most familiar features of life and one of the clearest cases where perception is doing active work. By the time the visual signal continues onward from the retina and into the brain, colour has already begun to separate from mere wavelength. It has become a structured code carried in parallel with brightness, contrast, and other features. Later stages of processing will integrate those signals into surfaces and objects, so that the world does not appear as a scatter of floating patches but as cups, walls, pages, leaves, hands, shadows, and faces, each seeming to possess its own stable look. That stability is another construction, and it depends not only on colour, but on how the visual system combines edges, depth cues, motion, and timing to make the world appear sharp, solid, and still enough to trust from one moment to the next. That stability is one of the most convincing illusions your visual system ever produces. You open your eyes and the world appears complete. The edges of objects seem clean, surfaces look solid, the room seems laid out in an orderly way, the table stays where it is. The lamp looks like one object rather than a scattered set of colours and highlights. Even when you move your eyes quickly from one thing to another, the world does not appear to jerk and smear the way a camera might if someone shook it during exposure. It feels steady, detailed, and dependable. That feeling is so strong that it is easy to assume it must simply mirror the world as it is, as though sharpness, solidity, and stillness were handed directly to us by the optics of the eye. But that is not quite what is happening. Those qualities are assembled from several different kinds of information, and the assembly is far more active than ordinary experience suggests. To begin with sharpness, it helps to remember something slightly inconvenient about the retina. It is not equally detailed everywhere. The highest acuity lives in a small central region called the fovea, where cones are densely packed, and the wiring preserves fine spatial information. This is the region you use when reading small text, inspecting a face, threading a needle, or discovering that what you thought was a harmless speck on a shirt is in fact a much more committed stain. The rest of the retina is less precise. Peripheral vision is excellent for detecting movement, general layout, and broad shapes, but it is not remotely as detailed as central vision. If the entire visual field were presented to consciousness, with the actual detail available at each retinal location, you would not experience the world as uniformly sharp. You would experience one small region of high detail surrounded by much coarser information, and yet that is not how it feels. When you look at a room, it seems as though all of it is there at once in roughly equal clarity. This is one of the visual system's most successful pieces of stagecraft. Your eyes move constantly, making rapid jumps from place to place. Each jump brings a different part of the scene onto the fovea, allowing detail to be sampled in sequence. The brain then combines these samples with broader peripheral information and with memory of what was just seen. The result is a stable impression of a detailed world. You do not feel yourself building it piece by piece, because the building happens quickly and automatically. The world feels ready-made. In reality, you are scanning it. This scanning is not occasional, it is continuous. Even when you think you're staring steadily at one point, tiny eye movements persist. Larger movements called saccades carry your gaze from one target to another. During reading, these jumps happen several times each second. During ordinary looking around, they help gather detail from objects of interest, shift attention, and keep the retinal image fresh. Without them, parts of the visual scene would fade as neurons adapted to unchanging input. So the visual system solves several problems at once. It points the sharpest region of the retina where detail is needed, it avoids stagnation, and it integrates the results so smoothly that you're left with the impression of a continuous, fully resolved scene. There is another trick hidden in those eye movements. During a saccade, the image of the world sweeps rapidly across the retina. If you were aware of the raw retinal input during that interval, the world should appear as a blur or smear every time your eyes moved, but normally it does not. One reason is that visual sensitivity is briefly reduced around the time of the movement. Another is that the brain uses signals related to the eye movement itself to help distinguish self-generated motion from motion in the world. In effect, the system knows that the eyes are moving and discounts the resulting image shift. This helps keep the world visually stable. Otherwise, every glance from the page to the window would look like a small earthquake. The same general principle applies when you move your head or body. The image on the retina changes constantly as you walk, turn, lean, or nod. Yet the room still appears stable. Part of this comes from information outside the eye. The brain receives signals from muscles, balance organs, and movement commands. It knows something about how the body is moving. It combines that with the changing retinal image and infers what belongs to your own motion and what belongs to motion out in the world. If you turn your head and the entire scene shifts across the retina in a way consistent with your own movement, the world is judged stable. If one object shifts differently from the rest, that object may be perceived as moving. Stability therefore depends not on the retinal image staying still, because it rarely does, but on the brain correctly accounting for why it is changing. Sharpness also depends on contrast more than people usually realise. A scene with poor contrast can feel soft even if the optics are fine. Edges become clear when light changes across space in a way the retina can emphasise. A black letter on white paper is easy to see, not simply because the letter exists, but because the difference between letter and page creates strong local contrast. A pale grey pencil mark on slightly off-white paper is much harder to notice because the contrast is smaller. The world seems sharp when edges are available to be detected and enhanced. In mist, fog, or dim lighting, contrast falls and the world softens. This is not only because less light arrives, it is because the distinctions that define boundaries become harder to extract. That brings us to solidity. A table does not merely look like a patch of colour, it looks like an object with shape, volume, and continuous surfaces. A cup looks cylindrical. A face looks three-dimensional. A room appears laid out in depth rather than as a flat collage pasted on the inside of your eyes. Again, this does not come for free. The image on each retina is fundamentally two-dimensional. It is a pattern of light spread across a surface. From that pattern, the visual system has to infer the arrangement of solid objects in space. It does this using many cues at once. Some of those cues come from having two eyes. Because your eyes are separated in space, each receives a slightly different view of the world. Nearby objects project more different positions in the two eyes than distant ones. This binocular disparity provides powerful information about depth. The brain can compare the two retinal images and recover aspects of three-dimensional structure from the differences. This is one reason why depth can feel so immediate at close range. It is not guessed from one image alone. It is supported by a built-in comparison between two viewpoints. But binocular disparity is not the whole story, because people can still perceive depth with one eye. That tells us there are many monocular cues as well. Perspective is one. Parallel lines in the world project toward convergence in the image as they recede, so roads and hallways seem to narrow with distance. Relative size is another. If two objects are known or assumed to be similar in actual size, the smaller retinal image is usually taken as the more distant one. Occlusion is especially important. If one object blocks part of another, the blocking object is usually judged nearer. Shading matters too. The way light falls across a surface can suggest curvature, bumps, hollows, and orientation. Texture gradients, focus blur, atmospheric haze, and motion parallax all contribute. When you move, nearer objects shift across the field of view more rapidly than distant ones, and the visual system uses that difference to judge depth. Taken together, these cues allow flat retinal images to be interpreted as a world of solid objects. The interpretation usually works so well that we forget it is an interpretation, yet it can be manipulated. Draw a few lines with proper perspective and shading, and a flat picture can look like a corridor or a cube. Present conflicting depth cues, and perception becomes uncertain or flips between possibilities. The solid world you experience is the result of the brain making the best use it can of several imperfect hints. It is a stable guess that is usually good enough to guide action. Solidity also depends on grouping. The visual system has to decide which bits of colour, edge, texture, and motion belong to the same object. A cup on a table may include highlights, shadows, curved edges, a handle partly overlapping the body, and perhaps a stripe or printed design. All of these retinal features must be grouped into one object rather than treated as unrelated scraps. The system does this by using principles such as proximity, similarity, continuity, and common motion. Parts that move together tend to belong together. Edges that align smoothly are likely to form one contour. Regions enclosed by boundaries tend to be taken as surfaces. Nearby elements with similar properties may be grouped into a single whole. These strategies are not philosophical positions. They are practical habits of a system trying to identify objects quickly in cluttered scenes. This is one reason why camouflage can work so effectively. If an animal's pattern disrupts its outline and blends with the surrounding textures, the visual system has trouble grouping the right features into a separate object. The world remains visible, but the object vanishes into the scene because the cues for grouping and boundary detection have been weakened or misdirected. The same thing happens in a much less dramatic way when you fail to notice your keys on a crowded surface because their shape, colour, and shadows are not separating themselves clearly from the background. The object is there. The visual system has simply not yet grouped the right evidence into one meaningful unit. Surface continuity is another major factor in solidity. The brain expects objects to occupy continuous space. If part of a chair is hidden behind a table, you do not usually experience the chair as having been sliced into disconnected fragments. You assume the hidden parts continue behind the occluding object. This ability to perceive completed forms, even when some information is missing, is essential for navigating a cluttered world. Without it, every partially blocked object would become a mystery. Instead, the visual system fills in likely continuity based on contours, alignment, and familiar shape patterns. It is not inventing recklessly. It is making educated guesses that are usually right. The blind spot offers a nice example of how far this constructive tendency goes. Each eye has a region where the optic nerve leaves the retina, and there are no photoreceptors. In raw retinal terms, that means a small patch of missing information. Yet under normal conditions, you do not see a hole floating in your visual field. The brain fills in the missing region using surrounding context and information from the other eye when available. This is not because there is no missing data. There is. It is because the system is more interested in preserving a coherent world than in faithfully displaying every gap in its own hardware. Stillness, like sharpness and solidity, is also constructed from active correction. The world seems still not because the retinal image is still, but because the causes of change are sorted appropriately. If your eyes move, the system treats that differently from object motion in the scene. If your body sways slightly while standing, compensatory mechanisms help stabilize gaze. The vestibular system, which senses head motion through the inner ear, contributes to reflexes that move the eyes in the opposite direction of head movement. This helps keep the image of the world from sliding too much across the retina when you walk or turn. Without such reflexes, vision would be far less stable and far more nauseating than most of us care to imagine before bed. Perceived stillness also depends on temporal integration. The visual system does not report every tiny fluctuation separately. It combines information over short spans of time, smoothing some changes and emphasizing others. This is why a rapid sequence of still images can produce the experience of continuous motion in film or animation. It is also why brief interruptions, blinks, or momentary losses of detail do not normally shatter the continuity of the world. The brain is not simply taking snapshots and laying them side by side. It is integrating across time to create a stable perceptual present. That integration is selective. Changes judged important, such as a moving object crossing your path, can be highlighted. Others, such as the momentary darkness of a blink, are largely ignored. You blink thousands of times a day, temporarily blocking light from entering the eye, and yet the world does not appear to vanish and return with each blink. Part of that is because blinks are brief. Part of it is because the visual system discounts the interruption. If every blink were experienced in full, daily life would feel like a poorly managed light show. The world also appears more stable, because the brain is willing to assume continuity, unless given good reason not to. Objects tend to persist. Surfaces tend not to dissolve when you look away for half a second. Rooms tend to remain arranged as they were a moment ago. These expectations are usually sensible. They let the system preserve identity over time. The mug on the desk remains the mug on the desk even if your eyes move away and back, or if the lighting changes slightly. This is object constancy in a broad sense. It helps explain how the world can seem dependable, even though the sensory input is always changing with movement, viewpoint, and illumination. That constancy can, however, be exposed by certain failures. Change blindness is a striking case. If a visual change occurs during a disruption such as a blink, a brief cut, or a distracting event, people can miss surprisingly large alterations in a scene. A person can change clothes between shots, a building can disappear, a prominent object can shift, and the observer may not notice immediately. This seems absurd until one remembers how much of the stable visual world is built from assumption, selective attention, and sparse high-detail sampling. We do not store or monitor every feature of the scene with equal precision. We maintain enough structure for useful action, and we update what matters most. That is not a weakness so much as a sensible economy. A system that attempted to preserve every local detail continuously and consciously would be inefficient beyond belief. Instead, the visual system builds a world that is good enough, stable enough, and detailed where needed. It lets you trust the floor, find the cup, read the page, recognize the face, and notice the moving car. It does not owe you a complete internal replica of everything in view. It owes you a workable world, and most of the time it delivers one with impressive skill. Even the sense that objects are made of solid stuff depends partly on how surfaces behave under light and motion. Stable edges, consistent shading, and coherent movement all support the impression of a single enduring object. If those cues are disrupted, solidity weakens. A transparent reflection in a window can look ghostly, because its edges and depth cues do not behave like a normal surface. Heat shimmer can make solid objects appear unstable, because the light paths are fluctuating. Mirrors complicate objecthood because they preserve directional information without offering an actual object where the apparent one seems to be. Under ordinary conditions, though, the visual system uses coherence across many signals to conclude that the world consists of solid surfaces laid out in stable space. So the room appears sharp because high detail is sampled and integrated, because contrast is enhanced, and because the eye is constantly directed toward what matters. It appears solid because depth cues, grouping principles, surface continuity, and object constancy all work together to turn a shifting pattern of light into a world of things. It appears still because self-motion is discounted, reflexes stabilize the image, timing is integrated, and continuity is assumed unless evidence demands revision. None of this means the world itself is unreal. It means that the form in which the world becomes available to you is heavily processed, and all of that processing takes time. Not much in everyday terms, but not zero either. Light travels, photoreceptors respond, retinal circuits compare, signals move onward, and the brain assembles a scene that feels present and immediate. The strange thing is that by the time you consciously experience the sharp, solid, stable world in front of you, the physical events that gave rise to that experience have already happened a little earlier. That earlierness is one of the strangest facts about seeing, because almost nothing in ordinary experience prepares you for it. Vision feels immediate. You look at a hand moving in front of your face, and it seems present in the simplest possible sense. You see a cup tipping, you catch it, and the whole event feels as though the seeing and the world were happening together in one neat package. A bird crosses the window, and it appears to do so right now. Someone speaks, and their expression seems to arrive with the words, "The room is there, the light is there, your sight is there," and common sense stitches those things into one moment. Yet physically, that is not what is happening. There is always a delay, however small, between the event in the world and your conscious experience of seeing it. The reason begins with something simple. Information takes time to travel. Light has to leave a source or a surface and reach the eye. That part is extraordinarily fast over everyday distances, so fast that it is not where most of the noticeable delay comes from, but it is still not zero. A lamp on the table sends light to your eye after a tiny interval. Light from the moon takes more than a second. Sunlight takes several minutes. Starlight may have been on its way for years before it enters a telescope or a human eye. So even before biology becomes involved, vision is already about reception after an event, not contact with an absolute present. You never see something until light from it or about it has arrived. At the scale of a room, though, the travel time of light is so short that it hardly matters for behaviour. The more substantial delay comes after the light gets there. Photons must be absorbed by photoreceptors. The light-sensitive molecules in rods and cones must change shape. Chemical cascades must unfold. Ion channels must close. Membrane voltages must shift. Neurotransmitter release must change. Bipolar cells must respond. Horizontal and amacrine interactions must shape the signal. Ganglion cells must generate impulses. Those impulses must travel along the optic nerve to the brain. Then multiple brain regions must receive, relay, compare, and integrate that information into something like a coherent visual experience. Each stage is quick, but none is magical. Each takes time because it consists of physical processes occurring in cells, across synapses, along membranes, and within networks. That means the world you consciously experience as visible is always slightly old. Not old in any dramatic or troubling sense. You're not wandering around in a museum of badly outdated moments. The delay is small enough that the world still feels present and useful, but it is there. By the time you become aware of a visual event, the event itself has already happened, and the sensory machinery has already been busy with it for a little while. Sight is not a window opening onto the immediate now. It is a reconstruction based on recent input. This becomes easier to appreciate if we compare vision with simple mechanical events. Imagine touching a hot surface. Heat reaches receptors in the skin. Signals travel along nerves. The spinal cord and brain respond. You experience the touch and pain after the physical contact has already begun. No one is especially surprised by that. The nervous system takes time. Vision is no different in principle, but because light travels so fast and because the experience feels so seamless, we're more inclined to think of seeing as instantaneous. It is not. It is simply fast enough to create the impression of immediacy. How long is the delay? There is no single number that covers all of visual experience because different pathways and different tasks take different amounts of time. Some visual responses can influence behaviour very quickly. reflexive eye movements, simple motion-related reactions, and coarse detections of change can occur on shorter timescales than detailed recognition or conscious judgment. The processing involved in noticing a flash, identifying a face, reading a word, or appreciating a colour shift is not identical. Even so, the broad point remains. Conscious visual awareness lags behind physical events by a small but real amount, often on the order of tens to hundreds of milliseconds, depending on what exactly is being measured and how it is defined. That may sound trivial, but it creates an interesting problem. If the nervous system is always a little behind, how do we manage to interact with moving things so effectively? How do you catch a falling object, hit a ball, avoid a cyclist, or even just track a hand gesture in conversation if what you see is always slightly in the past? One answer is that the brain is not merely reporting what has already happened. It is constantly making short-term predictions about what is likely to happen next. It uses recent motion, current context, and learned expectations to estimate where things are going. In effect, the visual system helps compensate for its own delay by getting ahead of itself. This predictive aspect is easier to notice in sports, where timing becomes unforgiving. A batter cannot wait for a fast-moving ball to arrive visually in some perfect conscious present, and then leisurely decide what to do. By the time the conscious impression is fully formed, the opportunity would largely be gone. Instead, the brain relies on ongoing prediction based on trajectory, speed, body movement, and experience. Something similar happens in much smaller ways all the time. When you reach for a moving object, cross a street, or even shake hands, your actions are guided by a world model that is being updated and projected forward rather than merely replayed. There is a nice irony in this. We speak of living in the moment, but perception itself is always slightly after the moment and trying to catch up by anticipating what comes next. The present, as experienced consciously, is already a constructed interval, not a razor-thin physical instant. The brain appears to gather information across short spans of time and integrate it into a perceptual now that is useful for action. That now is close enough to reality to function, but it is not the same thing as the exact physical edge of events. This becomes particularly evident when timing information from different senses has to be aligned. Light and sound do not travel at the same speed. Watch someone across a large field striking wood with an axe, and you may see the impact before you hear it. Yet at conversational distances, the visual and auditory signals are usually close enough in arrival time that the brain can bind them into one event. Even then, the nervous system still has to process each stream. Vision and hearing have different transduction mechanisms, different pathways, and different processing times. Still, your experience is usually one unified moment. That means the brain is doing temporal coordination, allowing signals that arrive and are processed on somewhat different schedules to be treated as belonging together. Speech is a perfect example. When you watch someone talking, the movement of their lips and the sound of their voice feel synchronized under ordinary conditions. If the timing is shifted artificially, as in badly dubbed video, the unity breaks and the mismatch becomes obvious. But within a certain range, the brain tolerates and corrects discrepancies, binding sight and sound into one event. This suggests that perception is not built from infinitesimal instants, lined up with perfect precision. It's built from temporal windows, short intervals over which the system decides what belongs together. Vision itself likely depends on such windows. A moving object is not detected from a single, frozen, retinal state alone. Motion requires comparing states across time. Even the sense of continuity in film depends on the fact that the visual system integrates sequences of images rather than treating each one as an isolated world. If perception had no temporal smoothing, the visible world would be far more fragmented. If it had too much, we would lose sensitivity to rapid change. So the system balances integration against resolution, gathering enough over time to create stability while still remaining responsive to events. The cost of that strategy is that some of what we consciously experience as present is already the result of integration over a recent interval. This does not mean that the brain waits passively for a long time and then delivers an old summary. It means that awareness may emerge from ongoing processing that combines information over short stretches rather than assigning every event to a single exact physical instant. The perceived now is not a mathematical point. It is more like a narrow band of recent time woven into a usable scene. This helps explain why certain illusions of timing are possible. A flash followed by a moving object can be perceived in ways that suggest the brain is revising how events are assigned in time. In some experiments, later information seems to influence how earlier moments are consciously experienced, at least within short intervals. That does not mean the future literally changes the past. It means the brain may wait just long enough to assemble a more coherent interpretation before committing to experience. Conscious sight may therefore involve a little bit of editorial delay, a brief period during which incoming events are organized into the most sensible story available. This editorial character also appears in the phenomenon of flash lag. If a moving object and a briefly flash stationary object are physically aligned at one moment, the moving object is often perceived as slightly ahead of the flash. There are different ways to interpret why this happens, but one influential idea is that the visual system is in some sense extrapolating the position of moving objects to compensate for processing delay. The system expects continued motion, and therefore represents the moving object slightly ahead of where the raw, delayed input alone would place it. Again, perception is not merely a report. It is a best effort guess shaped by recent history and probable continuation. The same need for compensation exists in your own movements. When you turn your eyes or head, the visual scene on the retina shifts dramatically, yet the world appears mostly stable. Part of that stability requires timing. Signals about the movement of the eyes and head must be coordinated with incoming visual information so that the brain can distinguish self-caused retinal motion from world motion. If the timing between these signals is disrupted, the world can appear unstable or delayed. Normally, though, the coordination is so good that you move through the world without noticing how much temporal bookkeeping is involved. Even blinking reveals something about this delay and compensation. A blink blocks light from entering the eye for a brief time, and yet you do not usually experience the world as flickering into darkness several times each minute. Part of this is because blinks are short and because the visual system fills continuity across them. But it also suggests that conscious perception is not tied one-to-one to every moment of retinal input. Some interruptions are suppressed or ignored in favour of a more stable account of the world. The brain prioritizes continuity over strict reporting of each transient gap. This can sound as though perception is hopelessly indirect, but that would be overstating things. The visual system is delayed, yes, but it is also remarkably efficient. The delay is small enough that action remains coordinated and experience remains useful. In fact, much of the nervous system is built precisely to work under these constraints. Reflex pathways can respond quickly to looming threats. Eye movements can be guided by partial information before full conscious recognition occurs. Motor commands can be adjusted online as new sensory input arrives. The brain does not wait for a perfect finished picture before acting. It operates continuously with multiple overlapping streams of information, some faster and coarser, some slower and richer. This layered timing is important. Not all visual processing reaches consciousness at the same stage or for the same purpose. Some circuits support rapid orienting, helping you turn toward movement or sudden flashes. Others support fine recognition, allowing you to identify a face or read a word. Still others help guide movement even when conscious report is poor. There are patients with certain kinds of visual brain damage who can respond to visual stimuli they deny consciously seeing, a phenomenon that reveals how multiple pathways can process visual information differently. The tiny delay between reality and sight is therefore not just one bottleneck, it is a whole architecture of timing, with several streams working in parallel. There is another subtle consequence of delayed perception. When you decide that something happened at a particular moment, That judgment is itself the result of processing. This may be why our intuitions about simultaneity are less solid than they feel. Two events that are physically separated by small intervals may be perceived as simultaneous if they fall within the temporal binding window of the system. Events that are physically simultaneous but processed differently may not feel simultaneous unless the brain corrects for their differing pathways. Our conscious timeline is not a perfectly calibrated chronometer. It is a perceptual construction tuned for usefulness. Even the simple act of seeing your own hand move involves this. Motor commands are sent to the muscles. The hand begins moving. Visual feedback from the hand's new position takes time to arrive and be processed. Signals from muscles and joints also report the movement. The brain combines predicted consequences of the motor command with delayed sensory feedback to maintain the sense that the movement is yours and is happening now. If those signals are experimentally delayed, people notice something unsettling. The movement can feel oddly detached or mistimed. Normal agency depends partly on keeping all these delays within expected bounds. There is a practical beauty in how well this usually works. Your nervous system is constantly compensating for finite transmission times, integrating across short windows, aligning senses, predicting motion, discounting self-generated shifts, and presenting the outcome as a world that appears immediate. It does not tell you about the backstage effort because doing so would hardly improve your evening. It simply hands you a scene that feels current enough to live in. Still, the slight lateness of sight has philosophical consequences whether or not we dwell on them. It means that the visible world is never the world exactly as it is at the current physical instant. It is the world as recently delivered, recently processed, and slightly projected forward. The difference is usually too small to matter in everyday reflection, but it matters enormously for understanding what perception is. Seeing is not touching reality directly with the mind. It is constructing a workable present from signals that are already on their way to becoming past. And because that construction is so skillful, the moments when it slips become especially revealing. When motion appears where there is none, when a flash seems mistimed, when the brain fills gaps or predicts too boldly, when the world seems to shimmer, lag, or ghost, we get a glimpse of the machinery that is normally hidden. The tiny delay between reality and sight is not just a technical footnote. It is one of the reasons vision can be fooled, bent, or led into strange experiences that tell us as much about the brain's methods as they do about the world itself. That hidden machinery becomes easiest to notice when it stops being perfectly discrete. Most of the time, vision does its work so well that we never think about it. The world appears stable, coloured, sharp enough, and continuous enough that we simply get on with our lives. We reach for cups, read words, recognise faces, and avoid furniture with a level of confidence that would be almost suspicious if it were not so familiar. But every now and then the system shows its hand. A line looks bent when it is straight. A grey patch seems darker than an identical grey patch beside it. A bright shape lingers after you look away. A missing piece of the visual field quietly goes unnoticed because the brain has filled it in. These moments can feel like visual mischief, as though the eye and brain had decided to amuse themselves at our expense. In reality, they are far more useful than that. They reveal the rules by which seeing normally operates. Illusions are especially revealing because they are not random failures. They are structured mistakes, and structured mistakes tell you what kind of strategy a system is using. If a machine repeatedly gets the same unusual cases wrong, you learn something about how it is built. Vision is no different. The reason an illusion works is usually that the visual system applies a rule that is sensible in ordinary conditions but misleading in a carefully arranged one. In daily life, the rule helps more often than it harms. In the illusion, the rule is exposed. Take brightness and contrast illusions, which are among the clearest examples of the retina and brain preferring relative information over absolute values. Place two identical grey patches on different backgrounds, one dark and one light, and they may appear different in brightness even though the amount of light coming from the patches is the same. This can feel impossible at first. Surely if the physical stimulus from the patch itself is unchanged, it should look unchanged. But the visual system does not treat each patch in isolation. From the retina onward, it compares regions with their surroundings. A patch on a dark background is interpreted within one context, a patch on a light background within another. Local contrast changes the appearance. The system is effectively asking not just how bright is this region, but how bright is it relative to what is around it. In ordinary viewing, that is an extremely useful question because surfaces are usually seen under uneven illumination, and relative differences often tell you more about object boundaries and material properties than absolute light levels alone. This same preference for contrast helps explain why edges often look sharper than the underlying light gradient really is. At a boundary between a bright and dark region, retinal circuitry exaggerates local differences. The bright side may appear a little brighter, and the dark side a little darker right at the border. That enhancement makes edges clearer and objects easier to separate. It also means that carefully designed patterns can produce brightness bands, or false differences that are not physically present in the stimulus itself. Again, the system is not malfunctioning in a general sense. It is doing what it usually does well, emphasizing transitions in a world where transitions matter. Geometric illusions show a related truth in a different form. Straight lines can look bent, equal lengths can look unequal, and identical shapes can appear larger or smaller depending on surrounding cues. These effects often arise because the visual system is not only measuring raw retinal geometry, it is interpreting lines and contours in terms of depth, perspective, context, and likely structure. A pair of equal lines with different arrow-like endings may appear different in length because one arrangement suggests an outward corner and the other an inward one, and the brain's ordinary interpretation of depth and distance becomes entangled with the simple, two-dimensional drawing. In the natural world, perspective cues are useful. On paper, they can be weaponized. That is a useful way to think about many illusions. They borrow tools from normal vision and place them in situations those tools were not really designed for. A flat drawing suggests depth strongly enough that size judgments shift. A static pattern mimics cues the motion system treats as movement. Repeating shapes create unstable local comparisons that make parts of the image seem to shimmer when the eyes move. The illusion works not because vision is careless, but because it is economical. It uses rules of thumb shaped by the statistics of ordinary scenes. Under artificial conditions, those rules can be led astray. Motion illusions are especially striking because they reveal how much the visual system cares about change over time and how strongly it expects the world to behave in coherent ways. There are patterns that seem to drift or pulse even when they are entirely still. Some of these effects depend on tiny eye movements. Your eyes are never perfectly motionless, so detailed patterns with the right contrast arrangement can produce shifting signals across the retina that the motion system interprets as movement. The scene on the page or screen is static, but the interaction between the pattern and your own visual machinery generates the experience of motion. This can feel mildly unsettling, though usually in a harmless sort of way, like realizing a carpet has opinions. Other motion-related illusions reveal the predictive habits we discussed earlier. If the visual system expects a moving object to continue along its path, it may represent its position slightly ahead of where a purely delayed account would place it. Under certain circumstances, this leads to mismatches between stationary flashes and moving targets, or to impressions that movement started earlier or later than it physically did. What these cases show is that perception is not content merely to trail behind the world. It is trying to be useful in real time, and usefulness often means a little extrapolation. Then there are illusions of completion, where the brain fills in missing information so effectively that we barely notice it has done so. This brings us to the blind spot, one of the most elegant examples of vision quietly editing reality. In each eye there is a location on the retina where the optic nerve leaves to carry visual signals toward the brain. At that location there are no photoreceptors because the nerve fibers must pass through. From a purely optical point of view, that means each eye has a patch of the visual field from which it receives no direct information at all. If the visual world were presented to consciousness in a brutally literal way, you should perceive a whole. A small region should simply be absent, but you do not. Under normal conditions, the blind spot goes unnoticed. Part of the reason is that the blind spots of the two eyes fall in different places, so binocular vision often supplies missing information from one eye with input from the other. Yet even with one eye closed, the blind spot usually remains invisible in ordinary scenes. The brain fills it in using surrounding patterns, colours, and contours. If a line passes through the blind spot, it may appear unbroken. If a textured surface covers it, the texture may seem continuous. The system does not announce that data are missing and request your patience. It supplies a plausible completion and moves on. This is a beautiful example of what perception is trying to achieve. It is not trying to display the status report of every sensor. It is trying to deliver a coherent world. In most situations, that means hiding gaps rather than spotlighting them. The blind spot is not a defect that ruins sight, because the visual system is designed around it. It knows, in effect, that some information is unavailable there, and that the sensible thing is to infer continuity from nearby evidence. Most of the time, that inference is harmless because the world itself tends to be continuous. Straight edges continue. Surfaces extend. Patterns do not usually vanish into tiny holes for no reason, so the brain fills in what is likely to be there. Laboratory demonstrations of the blind spot are therefore so memorable precisely because they make the hidden gap undeniable. Present the right small object in the right place while one eye is closed, and it can disappear completely. A dot vanishes. A gap in a line is filled. A mark on paper drops out of existence if it lands in the blind spot. This feels uncanny, not because the blind spot is normally dramatic, but because it is normally so well concealed. The demonstration reminds you that part of what you take to be direct seeing is actually inference carried out with calm confidence. Afterimages reveal another layer of the same story, but this time the emphasis is on adaptation. Stare at a bright shape or a strong colour for a while, then look at a blank wall or close your eyes, and the shape may persist as a fading ghost. Sometimes it keeps roughly the same brightness pattern. Sometimes the colours appear reversed in an opponent way. A bright white shape may leave a dark afterimage. A red patch may leave a greenish one. These effects are not little pictures burned into the eye in the crude sense people once imagined, though intense light can, of course, affect tissue in dangerous ways, and that is not something to experiment with. Ordinary afterimages are usually the result of temporary adaptation in the visual system. At the photoreceptor level, prolonged stimulation changes the state of the pigments and the biochemical balance of the cells. A region exposed to strong light may become less sensitive for a short while. When you then look at a neutral surface, that adapted region responds differently from surrounding less adapted regions, creating a contrast that appears as an afterimage. Colour afterimages involve opponent pathways as well. If you stare at a strong red field, the mechanisms coding that chromatic direction adapt. When the stimulus is removed and you look at something neutral, the balance of activity shifts, and the complementary hue becomes visible. In effect, the visual system is revealing its own calibration process. What makes afterimages so interesting is that they are private evidence of adaptation. The world in front of you may now be plain and neutral, but your visual machinery carries a recent history within it. That history affects what you see. Seeing is not only about what is present now, it is also about what has just happened to the system itself. If vision were a perfectly passive recording device, past stimulation would not linger this way. Afterimages show that perception depends on receptors and circuits whose states evolve over time. This temporal dependence appears in other places too. Walk from bright sunlight into a dim room, and the world first seems dark, then gradually more detailed. Step back outside and the brightness can feel briefly overwhelming. These are not exactly illusions in the showy sense. but they arise from the same general principle. The visual system is always adapting its sensitivity to recent conditions. It is trying to remain useful across vast changes in illumination. The cost of that flexibility is that appearance depends partly on adaptation state. A grey room after darkness does not look like the same grey room after staring into noon light. Your eyes are not the same eyes in those two moments, at least not functionally. Colour constancy gives us a subtler case where seeing can go strange if the assumptions fail. Under normal conditions, the brain tries to separate the colour of the illumination from the colour of surfaces. This usually works so well that we believe the colours of objects are simply there, stable and obvious. But ambiguous lighting can make the system choose different interpretations. A surface may look bluish under one assumed illuminant and white under another. A dress in a photograph can split public opinion, not because half the population has abandoned reason, but because the image leaves room for different plausible assumptions about the light source. One viewer unconsciously discounts a cool light, another discounts a warm one, and the same physical stimulus yields different colour experiences. The illusion becomes famous because it makes private interpretation unusually public. There are also cases where the brain insists on seeing an object or figure where the stimulus is incomplete. A few strategic line segments can make you perceive a bright triangle whose edges are not really drawn. Broken contours can produce the impression of a complete shape standing in front of other elements. Faces can be seen in arrangements of windows, sockets, clouds, or toast that have no actual face in them. These examples are not all identical in mechanism, but they share a broad theme. The visual system prefers coherent objects over disconnected fragments. It fills gaps, imposes structure, and resolves ambiguity in favour of familiar wholes whenever the evidence allows it. This is usually efficient. It also means that under certain conditions the mind will provide a triangle, a contour, or a face that the raw stimulus only hinted at. That tendency is especially strong with faces because the human visual system is heavily tuned to them. We are social animals and faces matter. As a result, even sparse or accidental arrangements can trigger face perception. 2 dark spots and a line can be enough. This is charming when it happens in harmless places, and perhaps slightly alarming when it happens in the dark with a coat on a chair. Either way, the principle is the same. Perception is biased toward meaningful organisation. Some strange effects reveal not only the normal strategies of vision, but also its limits. In low light, rods dominate and colour fades. Fine detail falls away. Moving objects may be easier to notice than stationary ones. The world becomes both more uncertain and in some ways more dramatic because the system is operating near the edge of its sensitivity. In those conditions, a small error, a bit of noise, or a suggestive pattern can have outsized effects. Shadows seem animate. Shapes become ambiguous. The visual system is doing its best with fewer photons and lower precision. What feels eerie in a dark room is often just the ordinary machinery of perception working with incomplete evidence. There is an important difference, though, between everyday illusions and more serious disturbances of vision. An illusion is usually a case where the system interprets a stimulus in a lawful but misleading way, while otherwise functioning normally. Blind spots and afterimages belong to the regular design of the system. They are not signs that something is wrong. Pathological distortions, by contrast, can arise from disease, injury, drug effects, migraine, or neural disruption. Those conditions tell us other things about the visual system, but they are not required to appreciate the central point here. Even healthy seeing is full of inference, adaptation, filling in, and correction. The strange cases are not exceptions to a direct photographic mode of vision. They are windows into how vision works all the time. Perhaps the most unsettling thing about illusions is not that they fool us once we know about them, but that they often continue to fool us even after explanation. You can learn that 2 lines are the same length, that 2 grey patches are identical, or that a shimmering pattern is perfectly still, and yet the appearance does not simply obey your new knowledge. This gap between knowing and seeing is deeply informative. It tells us that visual perception is not under voluntary control in the ordinary sense. You do not choose how the low-level machinery interprets contrast or context. The circuitry is doing its job according to its own rules. Conscious thought can correct your judgment, but it does not reach back easily and rewrite the early stages of appearance. That is why illusions are so scientifically valuable. They let researchers infer the structure of the visual system by studying the conditions under which it departs from literal measurement. They also offer something philosophically useful. They remind us that the visible world is not merely received, it is assembled. The assembly is usually reliable, but reliability is not the same thing as directness. When the assembly goes strange, the hidden methods become visible. The blind spot shows that missing information can be covered by plausible completion. After images show that recent stimulation changes the system itself and alters subsequent seeing. Brightness and colour illusions show that context and comparison matter as much as local input. Motion illusions show that tiny eye movements, prediction, and temporal processing all shape experience. Geometric illusions show that depth assumptions and spatial heuristics influence what looks true. Completion effects show that the brain would often rather infer a coherent object than display fragments honestly. Put all of that together and a clear picture emerges. Seeing is less like copying and more like controlled interpretation. That controlled interpretation is still tethered tightly to the world. The point is not that vision invents reality freely. It does not. It is constrained by the incoming light, by the structure of the eyes, by the statistics of natural scenes, and by the practical demands of action. But within those constraints it is active. It sharpens, groups, predicts, corrects, fills, compares, and adapts. Most of the time, this produces a world that feels immediate and trustworthy. Occasionally it produces a ghost colour on the wall, a vanished dot in the blind spot, a bent line that refuses to straighten, or a still image that seems to crawl. Those are not embarrassments. They are brief disclosures of the rules, and once those rules are visible, one last question starts to feel unavoidable. If seeing is built from light, comparison, prediction, adaptation, and inference, then what exactly is the final thing we call seeing? What is this experience that feels so direct, so outward-facing, so tied to the world, and yet depends at every stage on hidden construction inside us? At the end of the trail, from photon to perception, what does it really mean for a universe full of matter and light to become a scene that is there for someone at all? And that is where the whole story becomes both simpler and stranger. Simpler, because by now the main physical chain is on the table. Light is emitted, objects borrow it, filter it, and return some of it. The eye gathers that returning light and forms an image on the retina. Photoreceptors absorb photons and turn them into electrical changes. Retinal circuits compare, sharpen, sort, and send signals onward. Deeper parts of the brain receive those signals and continue the work, combining motion, colour, depth, edge, memory, expectation, and context into something stable enough to guide action. In that sense, the answer to what happens when you see something is no longer mysterious in the vague, magical way it may once have been. It is a sequence of physical events carried out by matter under lawful conditions. But it is stranger too, because at the end of that sequence something appears that is not present at the beginning in any obvious form. A visible world comes into being for a subject. Not just light, not just signals. A world! That is the point where people often feel the ground shift a little beneath them. Up until now, the discussion has been comfortably mechanical. Photons travel, molecules change shape, cells alter their electrical state, neurons fire in patterns. All of that can be described in the language of physics and biology without much trouble. But none of those descriptions, taken alone, sounds anything like the thing itself as you know it from the inside. None sounds like the feeling of looking at a blue evening sky, or noticing the pale gloss of a ceramic mug, or watching tree branches move against a bright window, or seeing a face become recognizable in an instant. The physical account is real, and it is indispensable, but it does not feel like experience. Somewhere along the line, the world stops being a set of optical and neural transactions and becomes appearance. This is the point where people are tempted either to retreat into mysticism or to become so sternly material that they pretend there is no puzzle at all. Neither move is especially satisfying. It is not helpful to wave a hand and say that consciousness explains everything, because that merely renames the question. Nor is it very convincing to say that there is no mystery simply because the system is physical. Of course it is physical. That is what makes the problem interesting. Matter arranged in a certain way can do something remarkable. It can produce a model of the world so rich and immediate that the model is not experienced as a model. It is experienced as reality itself, outwardly laid before you. One useful way to approach this without getting lost is to keep asking what vision is for. The act of looking is not a decorative extra added to a universe that was otherwise finished. It is a biological strategy. Organisms that can detect light, distinguish objects, judge distance, track movement, and identify useful or dangerous things gain practical advantages. Over time, systems evolve that do those jobs better and better. At first, the task may be very simple. A light-sensitive patch that distinguishes day from night is already useful. A cup-shaped eye that provides directional information is better. A lens that forms a sharper image is better still. Layer in motion detection, contrast enhancement, color discrimination, and predictive processing, and eventually you get a creature for whom the world is not just brighter or darker, but structured, navigable, and full of meaningful objects. From that perspective, seeing is not about reconstructing the universe in perfect detail for philosophical satisfaction. It is about generating a useful world, a world where edges mark obstacles, faces matter, movement is urgent, surfaces feel stable, and hidden regularities become reliable expectations. That is why the final percept is selective. It does not contain every last fact carried by the incoming light. It contains what the system has learned to value, or at least what it has learned tends to matter for survival, action, memory, and behavior. This can sound slightly deflating until one realizes what an achievement it actually is. The brain is not trying to duplicate reality like a second cosmos folded inside the skull. It is trying to build a workable version of the world from limited data, quickly enough to be useful. And useful worlds have a very particular structure. They are object-centered. You do not usually experience your visual field as a matrix of local wavelengths, intensities, motion vectors, and depth probabilities. You experience cups, doors, trees, hands, books, clouds, faces, shadows, reflections, roads, and rooms. The visual system has turned many lower-level features into coherent things. This object-based structure is one of the most important parts of normal seeing, and it is so familiar that it can disappear into the background. But think what it means. A certain pattern of reflected light reaches the retina. That pattern changes as you move, as the object moves, as lighting shifts, and as your eyes scan different parts of it. Yet across those changes, the system maintains the identity of the object. That is still the cup. That is still the same person. That is still the page of the book, even though the angle has changed and the shadows have moved. The universe in the act of looking is not a collection of separate frames. It is a stream of stable things. This stability depends on memory as much as on sensation. The brain does not meet each moment as if it had never seen anything before. It carries accumulated knowledge about shapes, materials, lighting, faces, places, movement, and causality. Those expectations influence what is seen, not in a mystical sense, and not usually in a way that lets you simply imagine whatever you please into existence, but in the quieter sense that interpretation is guided by what the system has learned from past encounters. A shiny highlight on curved metal is recognized as gloss because the brain has learned what such light patterns usually mean. A face can be identified quickly because the system has deep familiarity with facial structure. a room still appears room-like in dim light, because incomplete evidence is supplemented by prior understanding. Looking, then, is never a passive receipt of the present alone. It is the present meeting a prepared observer. This is why recognition can feel so immediate. You do not consciously infer that the thing before you is a chair by considering all possible alternatives and weighing their probabilities like a particularly diligent detective. The object simply appears as a chair. But that simplicity is the end product of a great many learned regularities built into the system. The visual brain has become exquisitely good at mapping certain patterns of input onto stable categories. In that sense, the universe in the act of looking is not just light becoming sight, it is light becoming meaning. There is something slightly humbling about that. We often imagine ourselves as detached observers confronting a world that simply presents itself, but the visible world you know is one that has been negotiated between incoming physical events and the structure of your own nervous system. That does not make it unreal. On the contrary, it makes it the only form of reality you can practically inhabit. The external world constrains perception at every stage. Objects, light sources, surfaces, distances, and motions are not optional. Yet the mode in which that world becomes available to you depends on the kind of creature you are. Another animal with different eyes, different spectral sensitivity, different motion processing, and different neural priorities would inhabit a different visible world while living in the same physical environment. A bee approaching a flower, a cat watching at dusk, a bird navigating by cues we do not consciously register, all are engaged with reality, but not with the same reality as experienced. Looking is species-specific, even when the universe is shared. Human vision, then, is a compromise. It is not the final truth about light. It is not the complete inventory of what electromagnetic radiation can do. It is a highly adapted way of turning a certain range of physical information into a world rich in surfaces, colours, textures, faces, movement, and depth. That range is narrow compared with all that exists. We do not directly see radio waves, infrared, ultraviolet, or X-rays. We do not directly perceive polarization the way some creatures do. We do not carry eyes that survey all directions at once or detect every flicker rate equally well. Yet within our limits, the visible world is astonishingly rich. A narrow band of light becomes enough for landscapes, books, gestures, moonlight, water, skin, smoke, glass, leaves, snow, and fire. The universe does not give us everything, but it gives enough to make a life. And a life, importantly, is lived not in raw sensation, but in scenes. What you actually experience most of the time is not isolated colour or detached brightness, but a world arranged around action. You see what you can reach, avoid, follow, read, grasp, recognise and remember. The floor is beneath you, the door is over there, the kettle is on the counter, the page is in front of you, the other person is looking this way, the road continues ahead. Vision is full of spatial structure because behaviour demands it. A world without such structure would be useless. So the universe in the act of looking becomes not merely visible but actionable. Objects are not only there, they are there at distances, in relations, under possible movements, within possible futures. That future-oriented quality is easy to miss, but it matters. Vision is not content simply to tell you what has happened. It is constantly preparing what might happen next. A moving object is tracked because it may continue moving. A step is judged because your foot is about to land. A face is read because an expression may change. A road is scanned because a bicycle may enter from the side. This is why prediction is woven into sight. The visual world is not a museum of completed facts. It is a live environment in which the next moment matters. In that sense, looking is not only about the present scene, it is about the immediate future of the scene and of you within it. This also helps explain why conscious seeing feels outward and unified, rather than inward and piecemeal. If the system constantly presented you with separate reports from different processing stages, you would be paralyzed by bookkeeping. Instead, it gives you the final practical summary. Not photons on the retina, not firing rates in ganglion cells, not contrast maps, not depth cues in isolation, but the cup on the table in front of you, the moving hand, the open book, the moon beyond the curtain. This summary is not false, it is compressed. It is the world translated into terms a body can use. There is a quiet elegance in how little of the underlying machinery needs to become visible for the system to work. You're not generally aware of your pupils adjusting, your lens accommodating, your eyes making saccades, your photoreceptors adapting, your retina comparing center and surround, your brain discounting your own movements, or your color channels adjusting for the likely illuminant. You're aware of the room. That is the point. The machinery hides itself so the world can appear. If the tools announce themselves constantly, the act of seeing would be far less useful and much less restful. One could hardly get through breakfast if every glance came with a detailed status report on retinal gain control. And yet, sometimes the machinery does become visible, as we have seen. In illusions, after images, blind spots and perceptual delays, the hidden work peeks through. Those moments are valuable because they remind us that the visible world is not simply given, it is made. Made lawfully, made reliably, made under pressure of evolution and immediate need, but made all the same. The world as seen is a collaboration between external physics and internal construction. The photons do not carry little labels saying face, window, danger, ripe fruit, or evening sky. The nervous system supplies those categories. It turns variation in light into a meaningful scene. This does not reduce the beauty of seeing. If anything, it deepens it. There is a special kind of wonder in realizing that when you look at something ordinary, almost absurdly ordinary, a cup, a page, a hand, a patch of wall in late light, you are witnessing a meeting between the cosmos and a nervous system that has learned how to turn that meeting into a world. Light leaves a source, touches matter, enters an eye, alters molecules, moves charges, excites cells, spreads through circuits, and finally appears as something laid out before you. Not as code, not as chemistry, but as the visible world itself. That visible world is never total. It leaves much out. It simplifies. It stabilizes. It pretends continuity where there is sampling, immediacy where there is delay, solidity where there is inference, and directness where there is construction. But it does so not to deceive in any malicious sense. It does so because that is what makes life possible. A perfectly literal display of all incoming data would not be truer in any useful way. It would be unusable. Truth in perception is not about reproducing every physical variable without compression. It is about giving an organism the right structure for action in a lawful world. So when we ask what actually happens when you see something, in terms of physics, the answer begins with the electromagnetic radiation and ends with organized neural activity. But in human terms, it ends with a world that seems to stand outside you, lit and shaped and available all at once. A world you can enter with your attention, move through with your body, and remember later as though you had simply been there with it, which of course you had, though not in the naive way you might once have imagined. And perhaps that is the most satisfying place to leave it, not with the claim that sight has been fully explained away, nor with the claim that it remains untouchably mysterious, but with the recognition that seeing is one of those rare things that becomes more impressive the more concrete it gets. The ordinary act of looking is not made smaller by understanding photons, retinal circuits, or perceptual delays. It is made larger. The next time you glance around the room, or notice moonlight on a wall, or catch your own reflection in a window, and look slightly more thoughtful than you expected, it may help to remember what is really taking place. The universe is not just sitting there waiting to be looked at. It is actively arriving by light, and your body is actively turning that arrival into a scene. So here you are now, a little farther along than when we began, in a room or a bed or a chair somewhere under a ceiling, looking perhaps at a screen that borrows its own little share of the night's attention. Around you, light is still moving, surfaces are still returning it, eyes somewhere are still collecting it, retinas are still translating it, brains are still making worlds out of it, and in your own small corner of things, the visible universe has once again managed to appear quietly, reliably, and with far more work behind the scenes than it ever lets on. Sleep well wherever you are, and whatever light is still gently finding its way to you.